Look up. There's a faint smear of light in the dark, and it's not just distant, it's incoming. Every photon you see left Andromeda before human civilization began, yet that ancient glow is racing toward us, closing the gap between two giant galaxies. When Andromeda finally arrives, what will we discover inside it? And what will its collision rewrite about life, astronomy, and humanity's future? In the northern sky, a faint smear of light watches you back. Older than civilization, nearer than it looks, and that ancient glow is not standing still. It is already coming. Night falls, and the sky becomes a clock, turning with the Earth while the horizon holds its breath. Constellations sweep in clean arcs, and the familiar points of light keep their sharp, indifferent focus. Yet one presence refuses the rules of starlight, lingering as a soft blur that the naked eye cannot resolve. It looks small, almost accidental, until you remember what distance means out here. Every photon from that pale oval began its journey before our cities had names, before our histories learned to write themselves. What you're seeing is not simply far away. It is the past arriving on schedule. That blur is the Andromeda Galaxy, a giant spiral of stars and dust and unseen mass. It hangs above us like a quiet question. What is Andromeda truly like, and what does it mean that it is moving toward us? Across 2.5 million light-years, gravity has been working without pause, drawing our galaxies together with patient certainty. The motion is slow enough to mock a human lifetime, and relentless enough to define the future of the sky. This documentary follows that approach from the inside out, where beauty and danger share the same silhouette. We begin where Andromeda first unsettled the universe, when a harmless-looking smudge broke the old map of reality. Then we step closer, reading its structure through light, where spiral arms, dust lanes, and a crowded core hint at forces we cannot touch. In its halo we will find the ghosts of collisions past, faint streams and shells that confess how galaxies grow by taking. We will widen the frame to the local group, where neighbours abound in a gravitational conspiracy, and where empty space is never truly empty. From there, the story turns to the invisible scaffold that makes the visible possible, and to the dark matter that weighs on every prediction. We will watch a slow-motion cataclysm unfold across billions of years, where stars mostly miss each other, but galaxies do not. We will ask what survives when two spirals trade momentum, trade gas, trade identities, and what new galaxy is born from that long exchange. And we will return, again and again, to the most intimate question. Among 1 trillion suns, could life exist there? And what would it mean for us to share a future sky? Between Andromeda and the Milky Way lies a gulf so clean it feels impossible. A void where voyages become physics problems before they become dreams. If we never cross it, we may still witness its arrival, because the universe offers another way to travel, through time. As Andromeda brightens across the ages and the constellations rearrange themselves, astronomy becomes a kind of prophecy, written in spectra and motion. The closer it gets, the less the night will resemble the one we inherited. Andromeda is not merely a distant neighbour, it is a time-delayed message about how the universe builds, destroys, and rebuilds on scales that dwarf human history. The collision ahead is not a sudden apocalypse, but a lesson in cosmic patience, where change is the only constant. To understand what is coming, we must learn to think in the units the universe prefers: millions of years, billions of years, and the quiet certainty of gravity. We will move from a naked-eye smudge to a mapped giant, from ancient wreckage to future choreography. And when Andromeda finally fills the sky, we will ask what it changes, about life, about astronomy, and about humanity's place in deep time. As we prepare to journey millions of light years away to witness this cosmic marvel, let's ground ourselves for a moment. I'm fascinated by the idea of us all watching this from our tiny corner of the universe. Let me know in the comments what time it is where you are and whether you're watching this under sunlight or starlight. And if you're ready for the voyage, hitting that like button and subscribing tells me you're on board. Night returns, and the sky runs like a fast clock over our heads, sweeping constellations across a dark dome. In a time-lapse, the stars draw clean arcs while the horizon stays fixed, an illusion that hides Earth's steady rotation. Most lights remain sharp points, but one faint blur refuses to resolve into a single star. It hangs beyond the bright patterns, a pale smear that the unaided eye can catch on a clear, moonless night. Astronomers label it M31, the Andromeda Galaxy. Yet that name arrived late and carried a quiet revolution. What you see is not a point like a star, but a soft patch of light with edges that never quite decide. It feels close, like a thin cloud caught in starlight, and that false closeness lasted for centuries. That blur is also a time machine that does not announce itself, because it looks so ordinary. Each photon left Andromeda long before cities, before writing, before the oldest monuments rose from stone. The light crosses space for millions of years, then lands on a retina for a fraction of a second. In that moment, the present and the deep past overlap without warning. Your eye becomes the end of an ancient journey. The smudge is quiet, but its message is violent in implication. It says the universe is larger than any human scale, and it hints that distance can hide entire worlds. It also raises a question that sounds simple until you try to answer it. How do you measure a place you cannot reach? For most of history, the sky offered no clean edges, only gradations of brightness and haze. Without telescopes, the Milky Way looked like a river of milk poured across the heavens, brightening where star fields thicken. Andromeda looked like a stain, a faint oval that appears and disappears with humidity, eyesight, and patience. Ancient observers catalogued what they could, and the language was blunt because the data were blunt. Anything fuzzy became a nebula, a cloud, a patch, a place where stars failed to separate. Some thought these were weather in the heavens, luminous vapours drifting above the fixed stars. Others imagined star stuff not yet fully formed, a kind of celestial fog waiting to condense into suns. The limits of vision became a theory of the cosmos, and the cosmos seemed to cooperate by staying unresolved. When telescopes arrived, the problem did not vanish, it sharpened into conflict, because better optics created sharper mysteries. Glass lenses gathered more light, and mirrors grew larger and more precise, pulling faint objects out of the dark. Astronomers found more nebulae, and some showed spiral structure when photographed with long exposures. The spirals looked like pinwheels, delicate arms wrapped around bright cores, with dark lanes cutting through like smoke. Those lanes were not empty space, but dust, cold grains that block starlight and sketch the anatomy of a galaxy. The question became unavoidable and deeply personal for astronomers, because it challenged the scale of everything they had learned. Were these spirals small objects inside our own Milky Way, or were they separate stellar systems far beyond it? If they were inside, the Milky Way might be the whole universe, a single grand city of stars. If they were outside, the universe would explode in size overnight, and the Milky Way would become only one address. Distance was the missing number, and distance was the hardest number to get. Nearby stars shift slightly against the background as Earth moves around the Sun, a tiny seasonal wobble called parallax. It is pure geometry, but the angles are so small that even the closest stars barely budge. That parallax trick works only for close neighbours, and it fails quickly with increasing range because the baseline of Earth's orbit is limited. Astronomers built a ladder of methods, each rung calibrated by the one below, stretching from parallax to brighter and rarer beacons. The ladder was fragile, and every rung carried its own errors, from instrument limits to dust dimming to mistaken assumptions about stellar types. Yet the ladder was the only way to turn a smudge into a measured place, and measurement was the only way to end the argument. By the early 20th century, the Milky Way itself was still under debate, because even our home system was not yet mapped. Some evidence suggested it was enormous, far larger than earlier star counts implied, and that the Sun was not central. Some evidence suggested the Sun was off to one side, living in a suburb rather than the downtown of the galaxy. Globular clusters, dense balls of old stars, traced a structure that pointed away from us, like breadcrumbs leading to a hidden centre. Their distribution suggested a vast halo and a gravitational hub far from the solar neighbourhood. The galaxy was becoming a system with shape and scale, but its borders were uncertain, and uncertainty is fertile ground for competing stories. And if the Milky Way had borders, the spirals might be beyond them, waiting like distant cities across a dark sea. In 1920, the argument took a public stage in Washington, D.C., at a meeting of the National Academy of Sciences. It became known as the Great Debate, and it was not a polite disagreement dressed in academic language. Harlow Shapley argued for a vast Milky Way that contained the spirals as nearby objects, perhaps as gas clouds or small systems embedded within our galaxy. He used the distribution of globular clusters to claim our galaxy was huge, making outside galaxies unnecessary. He also pointed to novae and spirals that seemed too bright if the spirals were very far away, because brightness falls with distance. His position had an internal logic. If the Milky Way is immense, then the spirals can be local, and the universe stays compact. He could accept a big Milky Way more easily than a universe filled with other galaxies, because the latter demanded a new level of cosmic humility. Heber Curtis argued the opposite, and he came armed with spirals, photographs, and the stubborn geometry of flattened disks. Curtis saw the Milky Way as one galaxy among many, an island in a larger ocean, with other islands scattered beyond sight. He noted the dark lanes and flattened shapes of spirals, suggesting they were disk systems like our own seen from different angles. He emphasized that novae and spirals appeared faint compared with those in the Milky Way, implying great distance rather than small intrinsic power. Curtis also pointed to the high velocities measured in some spirals, derived from spectral shifts, which seemed extreme for local objects bound to the Milky Way. The debate hinged on limited data and imperfect classification, and both men could claim reasonable ground. Beneath the rhetoric was a deeper problem. Astronomy had reached the edge of what the instruments could settle. The great debate did not end with a verdict, because the universe did not yet offer one in numbers. The audience heard two coherent stories built on incomplete measurements, and the room had no decisive experiment to run. The tension remained, and it shaped the next steps of astronomy, because unresolved questions become missions. If someone could find a reliable beacon inside a spiral, the distance ladder could reach it. If that distance proved enormous, the island universe idea would win, and the Milky Way would lose its monopoly. The cosmos was waiting for a single kind of star, one that could speak its distance clearly. That star was not a new discovery, but a pattern hidden in plain sight, recorded on glass plates and overlooked in the glare of bigger theories. Henrietta Swan Leavitt worked at Harvard College Observatory, where women were often hired as computers to perform meticulous measurements. She studied photographic plates, comparing exposures taken nights or months apart, and she measured the brightness of variable stars with patient consistency. In the small Magellanic Cloud, she found Cepheid variables that pulsed with steady periods, brightening and dimming like cosmic heartbeats. These stars expand and contract because of a physical instability in their outer layers, a cycle driven by changes in opacity that trap and release heat. Leavitt realized the period of a Cepheid was linked to its intrinsic luminosity, the true wattage of the star. Longer period meant a brighter true star, regardless of how faint it looked from Earth. Leavitt's period to luminosity relation turned variability into a ruler, and it did so with elegant simplicity. Measure the period, infer the true brightness, compare with the observed brightness, and distance falls out through the inverse square law. It was a clean idea with enormous reach, and it did not require knowing every detail of the star's composition. Yet the relation needed calibration because you must anchor the scale with Cepheids, whose distances are already known by other means. That calibration depended on parallax and on careful corrections for dust, which can dim and redden starlight like smoke in a theatre. Even so, it was the hidden key that could unlock the spirals, because Cepheids are bright enough to be seen far away. A smudge could become a place if it contained Cepheids, and a place could become a chapter in a larger universe. Edwin Hubble arrived at Mount Wilson Observatory with access to the largest telescope of the era, perched above the haze of Los Angeles. The 100-inch Hooker telescope was a technological monument, a massive mirror that gathered light like a bucket gathers rain. With it, astronomers could resolve stars in nearby galaxies, if the galaxies were not too far and if the seeing was steady. Hubble targeted the Andromeda Nebula, still called a nebula in common usage, because language lags behind discovery. He searched for individual stars that change brightness in a regular way, the signature of Cepheids. The work required patience, repeated exposures, and careful comparison of plates under a blinking viewer that made differences jump out. The goal was simple and dangerous, because it threatened the size of the universe and the reputations built within it. In 1923 and 1924, Hubble identified Cepheid variables in Andromeda, and the identification was a turning point disguised as a pencil mark. He measured their periods, then used Leavitt's relation to estimate their true luminosities, translating rhythm into distance. The numbers forced a conclusion that could not be negotiated away, because they were not opinions but magnitudes and logarithms. Andromeda was far beyond the Milky Way, far beyond any plausible boundary Shapley could stretch without breaking his own evidence. It was not a small cloud of gas or a nearby star cluster, and it was not a minor appendage of our galaxy. It was a galaxy, a system of billions of stars comparable to our own, with its own dust lanes, star clouds, and central bulge. The distance estimate has been refined over a century, because better instruments and better physics keep tightening the ladder. Astronomers now correct for different types of Cepheids, for metallicity effects that subtly alter luminosity, and for interstellar extinction that dims the view. Yet the shock remains intact, because the order of magnitude did not change. Andromeda sits about 2.5 million light-years away, a number that turns the word nearby into a cosmic joke. That means the light entering your eyes tonight began its trip when early humans were learning to survive, long before agriculture and long before recorded history. It means the Milky Way is not the universe, but one member of a vast population. The word galaxy changed from a synonym for the Milky Way to a category of objects, and a category is always larger than a single example. The universe became crowded, and the crowd kept growing as telescopes pushed deeper. This was not just a bigger map, it was a new kind of reality, because scale changes meaning. If Andromeda was a separate galaxy, then the spiral nebulae scattered across the sky were likely galaxies too, each with its own stellar census. The observable universe suddenly contained millions, then billions, then trillions of galaxies, as later surveys revealed fields packed with faint smears. The scale of cosmic history expanded with the scale of cosmic space, because more space means more time for structures to form. Human stories became local, bound to one star in one galaxy, and even that star became one among hundreds of billions. Astronomy gained a new horizon, and humility came with it, not as philosophy but as measurement. The revelation also rewired the meaning of the night sky, because familiar lights became signposts to something larger. The Milky Way became one luminous disk among others, seen from inside, its bright band a perspective effect rather than a boundary. The smudges became external galaxies, each with its own structure and history, each rotating under gravity. Some were spirals like Andromeda, with organized disks and sweeping arms where gas forms new stars. Some were ellipticals, smoother and older, their stars moving in random orbits like bees in a swarm. Some were irregular, distorted by interactions, their shapes telling stories of past encounters. The universe gained variety, and that variety demanded explanation, because differences imply processes. How do galaxies form? How do they evolve? And what forces shape their fates? Andromeda was no longer a curiosity, but a neighbour with a biography written in starlight. Yet Andromeda is not only distant, it is dynamic, and motion can be measured even across millions of light-years. Even before the details were known, astronomers measured its motion by splitting its light into a spectrum. Spectra showed its light was blue shifted, meaning it is moving toward us along the line of sight, compressing wavelengths like a siren's pitch rising. The approach is slow on human timescales, but relentless on cosmic ones, because gravity does not tire. Gravity binds the local group, a small community of galaxies embedded in a larger cosmic web. The Milky Way and Andromeda are its dominant members, surrounded by smaller companions like the Triangulum Galaxy and dozens of dwarf galaxies. Two massive galaxies are already in a long fall toward each other, guided by dark matter halos that extend far beyond visible stars. That fact twists the opening mystery into a future tense, because the smudge is not only a relic but a warning. The smudge is not just ancient light arriving late, it is a sign of an encounter ahead, written into the geometry of orbits. Over billions of years, the two galaxies will distort, pass through, and eventually merge, their disks stretching into tidal tails that arc across space. Stars will mostly miss each other, because the distances between stars are vast compared with their sizes, and direct collisions are rare. But orbits will be scrambled, and gas will collide, shock and compress, turning calm reservoirs into starburst regions. New waves of star formation may ignite, and the night sky will be rewritten, not by a single event but by a slow choreography. The Andromeda we see is both a fossil record and a forecast, an ancient message that also points forward. So Chapter 1 ends where the old universe ended, at the edge of a mistaken assumption that once felt like common sense. The Milky Way is not the whole, and Andromeda is not a nearby cloud no matter how gently it glows. A single class of pulsing stars measured by a woman whose name was nearly hidden behind institutional habits broke the universe open. A debate that could not be settled by rhetoric was settled by distance, and distance has a way of silencing argument. The smudge became a galaxy, and the cosmos became a multitude, with room for countless histories we have not yet read. Now the question changes and it becomes more intimate again, because knowing what something is only opens the next door. If Andromeda is a galaxy, what kind of galaxy is it in detail, beyond the label and the distance? How is it built? How does it compare to the Milky Way, and what does it contain? From star clusters to dust lanes to a crowded central bulge. And if it is truly our nearest great neighbour, why is it headed our way? And what does that motion reveal about the invisible mass around us? The next chapter follows the smudge into structure, motion, and the long approach that has already begun. Now the question changes, and it becomes more intimate again. We have a distance and a name, but the object stays unreachable. We can chart Andromeda's anatomy with light, while touch remains impossible. Begin with orientation, because even size is a trick of perspective. Andromeda spans several degrees of sky, wider than the full moon by many times. In a dark rural sky, it can look like a soft thumbprint, brighter toward the centre and fading outward. In a city, it can vanish completely, its light diluted until it becomes background. Apparent size is not physical size, but it hints at a vast disk seen at an angle. That angle matters, because we are not looking face-on into a neat pinwheel. We see Andromeda tilted, with one side of the disk closer and the other receding. The tilt stretches features into an ellipse, and it stacks dust and stars along our line of sight. Even before we measure anything, geometry begins to edit what we think we see. Translate that smear into scale, and the numbers turn uneasy. Andromeda's stellar disk stretches roughly 220,000 light-years across. The Milky Way's disk is closer to 100,000 light-years in diameter. Our nearest giant neighbour is not just nearby, it is bigger. A light-year is already a strange unit, because it is distance disguised as time. When we say 220,000 light-years, we are also describing how long light would need to cross the disk. That is longer than the entire span of human civilization by orders of magnitude. It is a reminder that a galaxy is not an object you look at so much as a system you sample. Then widen the frame beyond the bright disk, because the visible galaxy is only the inner story. Around Andromeda lies a halo of stars and dark matter, extending far past the luminous edge. The halo is not a faint decoration, it is the main reservoir of mass. The shape we see is a small island inside a larger invisible continent. In visible light, the halo can seem like nothing at all, because it is too diffuse for the eye. Yet dynamically, it is everywhere. Its gravity holds the disk together and sets the speed of orbiting material. The halo's dark matter does not shine, but it leaves fingerprints in motion. In astronomy, motion is often the most honest evidence we can obtain. Classify the structure, because morphology compresses history into a label. Andromeda is a spiral galaxy, typed SAS-DOP in the Hubble sequence. It is unbarred, with moderately wound arms and a prominent bulge. The label is shorthand, but it points to rotation, gas dynamics, and ongoing star formation. The Hubble sequence itself has a history, because it began as a visual taxonomy before galaxies were understood as evolving systems. Early observers sorted forms the way naturalists sorted shells, by appearance first, then by inference. Today we keep the labels, but we read them differently. A spiral classification carries assumptions about angular momentum, gas content, and how the disk remained thin. Spiral arms are not rigid structures made of the same stars. They are patterns that move through the disk like traffic waves on a highway. Gas enters the wave, compresses, and forms new stars in bursts. Young, hot stars outline the arms, then drift away as they age. The physics behind the wave is subtle, because it is not a material arm rotating like a spoke. Instead, gravitational instabilities and orbital resonances can organize the disk into regions of higher density. Stars and gas orbit at different speeds depending on radius, yet the pattern can persist. The result is a galaxy that looks sculpted, even though its ingredients are always in motion. That mechanism explains why spiral galaxies look alive in some wavelengths and quiet in others. Massive blue stars shine briefly, then explode as supernova and enrich the gas. The disk becomes a cycle of collapse, ignition, and feedback. Andromeda's arms are a map of where that cycle is strongest today. Feedback is a kind of self-regulation, and it can be violent on local scales. Stellar winds and radiation push on surrounding gas, while supernova shocks heat and stir the interstellar medium. Some clouds are shredded while others are compressed into new rounds of star formation. The arms become not just a pattern, but an engine that reshapes its own fuel. But Andromeda's arms are also interrupted by darkness that is not empty space. Dust lanes cut across the disk, especially along the inner edges of the arms. Dust grains absorb and scatter visible light, hiding star-forming regions behind opaque curtains. The galaxy's most active nurseries can be the hardest to see in optical images. Dust is made of ordinary elements, carbon, silicon, oxygen, iron, assembled into microscopic grains. Those grains are born in the outflows of dying stars and in the debris of supernovae. In plain terms, dust is recycled stardust, drifting between stars in cold clouds. When it blocks our view, it is not an obstacle from outside, but part of the galaxy's own ecology. Shift to ultraviolet, and the story changes because UV favours the younger stars. UV light traces hot, short-lived populations that mark recent star formation. Regions that look muted in visible light can flare in UV if dust is thin. Regions that look bright in visible light can fade if they are dominated by older stars. Ultraviolet images can feel like a different galaxy entirely, because they isolate a brief moment in stellar lifetimes. A massive O-type star may live only a few million years, which is an instant on galactic timescales. Seeing UV bright knots is like catching sparks in a slow-burning fire. It raises a question: how many such bursts have already faded from view? Shift again to infrared, and dust stops being a blocker and becomes a beacon. Absorbed starlight heats dust grains, which re-radiate energy in the infrared. IR surveys reveal embedded star formation that optical telescopes miss. The same dust that erases detail in one band writes it back in another. In infrared maps, the disk can glow with a warm, granular texture, as if the galaxy is lit from within. Dark lanes in optical light become luminous ribbons, tracing where dust is thickest and most energized. This is not a contradiction, it is translation. Each wavelength reveals a different physical process. We learn Andromeda by learning how light interacts with matter. This is the first unease of the tour. We build a coherent Andromeda by stacking incompatible views. No single image is the galaxy, only a translation of photons through an instrument. The object remains distant, while our models grow intimate. Even the act of photographing Andromeda is a negotiation with faintness. Long exposures gather sparse photons, while careful calibration removes the glow of our own atmosphere and the noise of detectors. The final image can look effortless, yet it is assembled from patience and statistics. In that sense, Andromeda is always partly a construction, faithful but mediated. Move inward to the bulge, where the disk thickens into a crowded central swell. The bulge contains older stars on more randomized orbits than the thin disk. Its light dominates the inner region and mass finer structure. In Andromeda, the bulge is unusually prominent, hinting at an eventful past. A prominent bulge often suggests that the galaxy has been heated, stirred, or fed by mergers. Collisions can scatter stars into puffier orbits, and inflowing gas can build a dense central population. Bulges also tend to be metal-rich, because repeated generations of stars enrich the gas over time. In Andromeda, the bulge is a clue written in brightness. At the very centre sits a nucleus that refuses to be simple. Andromeda shows a double nucleus, two brightness peaks separated by a small distance. The effect is not two galaxies, and not two black holes of equal power. It is a stellar structure shaped by extreme gravity. On high-resolution images, the double nucleus looks like a subtle split. Two cores inside one core, like a candle flame that has forked. The separation is tiny on the sky, and it takes careful optics to resolve. Yet the implication is enormous, because it means the central region is dynamically organized. Something is shepherding stars into a pattern that persists. One leading explanation uses an eccentric disk of stars orbiting a central black hole. Stars linger near the slow point of their orbits, piling up into a bright peak. The true dynamical center lies near the other peak, where the black hole anchors the system. The double nucleus becomes a snapshot of orbital mechanics under intense tidal forces. Eccentric orbits are fragile in many environments because random encounters tend to smear patterns out. Near a supermassive black hole, however, gravity dominates so strongly that orbits can remain coherent. The stars move fast and the timescales are short compared with the rest of the galaxy. It is a small, sharp laboratory, embedded inside a vast, slow system. Name the central engine because it connects structure to fate. The supermassive black hole in Andromeda is called M31 It is quiet compared with active galactic nuclei, but quiet does not mean small. Its mass is estimated at roughly 1 to 200 million suns, larger than the Milky Way's central black hole. Quiet here means that it is not currently feeding at a high rate. Active galactic nuclei blaze when gas spirals inward, heats up, and radiates across the spectrum. In Andromeda, the central black hole is more like a banked fire than an open furnace. Yet its gravity is always on, and its past may have been louder than its present. Explain how we know, because the black hole is inferred rather than seen. Stars near the nucleus move fast, and their velocities can be measured from spectral shifts. The closer the star's orbit, the stronger the gravitational pull required. From those motions, astronomers estimate the enclosed mass and isolate the black hole's contribution. The technique relies on the Doppler effect, light stretched redward when a star moves away and compressed blueward when it approaches. With spectroscopy, those tiny shifts become speed measurements, and speed becomes mass through gravity. It is a chain of inference that sounds abstract, yet it is anchored in a simple idea. Fast orbits require a heavy center. When the mass is too concentrated to be stars, the black hole remains. This is another boundary between knowledge and contact. We can measure a black hole's mass across millions of light years. We cannot sample its environment directly, or watch a single orbit complete. We live on the far side of a time delay, reading dynamics from ancient light. Even the present we describe is layered, because different parts of Andromeda are seen at the same delayed moment. The photons left together, but they carry information from regions with wildly different internal timescales. A star's orbit near M31 can change measurably over centuries, while the outer halo evolves over billions of years. Our single image compresses those rhythms into one frame. Step back out to the disk, because the disk is where most of the galaxy's stars reside. Andromeda's disk is a rotating plane of gas, dust, and stars with a clear inclination to our line of sight. Rotation curves show that outer regions orbit too fast for visible matter alone. The missing mass points to a dominant dark matter halo. A rotation curve is a plot of speed versus distance from the center, and it carries a shock. In a simple system where mass is concentrated toward the middle, orbital speed should drop with radius. In galaxies, they often stay high, as if an unseen scaffold extends outward. Dark matter is the name we give that scaffold, real in effect, invisible in emission. That halo matters for more than bookkeeping, because it sets the galaxy's gravitational reach. It binds satellite galaxies and captures incoming debris. It shapes how Andromeda and the Milky Way fall toward each other. The merger story begins in halos long before disks touch. In a wide visualization, you could imagine the bright disk as a lantern, and the halo as the dark field in which it hangs. Satellites orbit within that field, tracing loops that can last for billions of years. When a small galaxy ventures too close, tidal forces pull it apart. The debris does not vanish. It becomes structure in the halo, written in faint stars. Count the stars, and the scale becomes personal again. Andromeda contains on the order of 1 trillion stars depending on how faint the census goes. The Milky Way likely holds a few 100 billion stars. Even conservative estimates make Andromeda a larger stellar metropolis. Yet a star count is not a population story without ages and chemistry. The disk hosts a mix of young and intermediate-age stars, with star formation continuing in rings and arm segments. The bulge and halo skew older, with many stars formed early in cosmic history. Metallicity gradients record where gas was enriched and where it stayed primitive. Metallicity is astronomy's blunt but powerful term for elements heavier than helium. Those elements are forged in stellar cores and in explosions, then mixed into the gas that forms new stars. A gradient means the galaxy did not form all at once, from perfectly mixed material. It formed in stages, with inner regions often enriching faster than the outskirts. In Andromeda, chemistry becomes a timeline you can map. Introduce globular clusters, because they are time capsules with sharp statistics. Andromeda has a rich system of globular clusters orbiting in its halo. Many are metal-poor and ancient, formed when the universe was young. Their orbits and compositions preserve evidence of early assembly and later accretion. Globular clusters are dense spherical swarms, hundreds of thousands of stars packed into a region only tens of light-years wide. They are among the oldest surviving structures in galaxies, and they resist disruption. When you see one, you are seeing a relic that has endured since near the beginning. In Andromeda, the sheer number of them hints at a long and hungry growth. Some clusters may have arrived inside smaller galaxies that Andromeda consumed. Tidal forces strip those satellites, leaving streams of stars and clusters behind. The halo becomes a graveyard of mergers, spread thin across enormous volume. In Andromeda, stellar streams and substructures show that growth did not happen smoothly. Those streams can be astonishing in deep images, faint arcs and ribbons curving around the galaxy like smoke trails. They are not artistic embellishments, they are the remains of real systems pulled apart by gravity. Each stream carries a memory of an orbit, and each orbit implies a past encounter. When we map them, we are reconstructing a crime scene written in starlight. The halo is also where the visible galaxy fades into uncertainty. Its stars are sparse, and their light is hard to separate from foreground contamination. Mapping requires deep surveys and careful statistics, not a single dramatic image. The result is a halo that reaches far beyond the disk, both in stars and in dark matter. Foreground contamination is not a minor annoyance, because our own Milky Way is always in the way. Countless nearby stars sit in the same line of sight, and distant background galaxies add their own noise. Astronomers separate populations by colour, motion, and spectra, building confidence one data point at a time. The halo emerges slowly, like a coastline appearing through fog. That extended halo changes how we define the galaxy's true size. The bright disk may be 220,000 light-years across, but the gravitational domain is much larger. The local group is a web of overlapping halos, not isolated islands. Andromeda's influence extends into the space we once called empty. In that web, between galaxies is not truly empty. It is a low-density environment shaped by gravity. Halos can overlap, and their outer regions can interact long before any visible collision. The Milky Way and Andromeda already share a dynamical relationship, even now. Their future encounter is not a surprise. It is a continuation of a long fall. Return to the spiral arms with this wider context, because arms are surface features on a deeper mass distribution. Density waves organize gas, but the halo sets the rotation and stability of the disk. Star formation depends on gas supply, and gas supply depends on past interactions. Even a calm-looking spiral can be shaped by old collisions. Andromeda's disk shows rings and asymmetries that suggest perturbations. Some features may trace encounters with companions like M32 and M110. Others may be relics of a larger merger in the past. The present structure is a compromise between rotation, gravity, and disruption. Rings can form when gas is nudged into resonances, collecting into bands where star formation becomes efficient. Asymmetries can persist for long periods, especially if the disk has been disturbed and is still settling. In images, these features look like gentle imperfections, but they are dynamical scars. The disk remembers being touched, even when it appears serene. This is the central tension of the chapter. We can map disk, bulge, arms, and halo with increasing precision. We still cannot walk there, or test a sample in our hands. Our tour is built from photons that left before our species kept records. There is also a deeper tension, quieter but persistent. Our measurements are precise, yet our intuition remains terrestrial. We speak of trillion star populations as if they were cities, but the distances between stars are vast. We speak of dust lanes as if they were clouds, but their grains are scattered through volumes that dwarf solar systems. The language is familiar, while the reality is alien. Tie the anatomy to the documentary's central question, because structure is not neutral. What is Andromeda truly like, and what will it mean for life and astronomy as it approaches? The answer begins with scale and mass, because mass drives the future. A larger disk and a heavier black hole do not threaten us directly, but the shared gravitational field will reshape both galaxies. Andromeda's approach is not a sudden impact. It is a slow tightening of orbits. The first pass will distort disks and trigger new star formation, while most stars avoid direct collision. Gas clouds will not be so lucky, and compressed gas can ignite starbursts. The night sky for future observers will become brighter, stranger, and more crowded. It is worth pausing on that counterintuitive detail. Stars almost never hit each other in a merger. The typical separation between stars is so large that even when galaxies overlap, most stars pass by unharmed. What collides is gas, because gas occupies space continuously and can shock, cool, and collapse. The fireworks of a merger are mostly about gas physics, not stellar impacts. But before we jump ahead, we need to read the present as evidence. Every dust lane marks cold material and hidden nurseries. Every globular cluster marks an early epoch of star formation. Every stellar stream marks a swallowed companion and a rearranged halo. Every measurement also carries a quiet philosophical weight, because we are studying an object we will never visit. We infer temperatures from spectra, ages from colour, and mass from motion. Then we stitch those inferences into a coherent body. If the galaxy is a fossil record, we are paleontologists working from light. The question becomes, what else is written there that we have not learned to read? Andromeda's present form is a fossil record, preserved in structure and motion. The disk suggests long-lived rotation, but the bulge hints at heating and upheaval. The halo's metal-poor stars suggest ancient building blocks, while its substructures suggest recent accretion. The double nucleus points to a central black hole shaping stellar orbits at the smallest scales. When you hold all these layers together, Andromeda becomes less like a picture and more like a biography. The visible disk tells you what it is doing now, while the halo tells you what it has done before. The bulge suggests chapters of disruption, and the nucleus reveals a gravitational anchor that has been present through it all. A galaxy is not a static thing. It is an ongoing negotiation between matter, motion, and time. End the tour with a final unease, because knowledge does not erase distance. We can measure Andromeda's diameter, classify its arms, and weigh its black hole. We still experience it as a faint smear, a message delayed by 2.5 million years. The closer we look, the more the gulf becomes part of the story. In that gulf, there is a strange intimacy, because Andromeda is both remote and connected. Its gravity already tugs on our local group, and its future is braided with ours. Its light reaches our eyes after a journey longer than humanity's entire story. When we look at it, we are looking at the past, and yet we are also looking at our own future sky. And that gulf sets up the next question, sharper than morphology. If Andromeda's structure is layered evidence, then what events built those layers? What collisions fed its bulge, seeded its halo, and rearranged its disk? The next chapter follows the fossil record backward into violence and forward into our shared fate. Andromeda looks calm at a distance, but its halo is a confession. Faint, sprawling, and crowded with the aftermath of old encounters. The pale smear that reaches our eyes from deep time is not just light, it is testimony. Those photons left when early humans were still painting caves, and they carry evidence of repeated violence written in starlight. The central question sharpens again, because the beauty is deceptive. What is Andromeda truly like? If its growth depended on destruction, galaxies do not assemble in silence, because gravity collects matter by taking it from somewhere else, and it rarely asks permission. In the local group, small galaxies orbit larger ones like moths around a lamp, drawn in by a deepening gravitational well. Over time, tides stretch them, strip them, and dissolve them into streams, while their dark matter halos are peeled away even faster. The result is not a clean edge, but a halo filled with debris, stars, clusters, and diffuse clouds that no longer belong to any intact system. This is galactic archaeology, and it works like forensics with imperfect witnesses. Astronomers cannot rewind time, and they cannot watch a merger unfold at human speed, but they can read motion, chemistry, and age. They also rely on statistics, because each star is one data point in a much larger pattern. Star by star, they reconstruct which populations formed together and which arrived later, even when the original galaxy has been erased. The halo becomes a crime scene where every orbit is a clue, and every chemical ratio is a fingerprint. Begin with kinematics, because motion remembers what light cannot describe, even when the stars are too faint for detailed portraits. Stars in a settled disk share ordered rotation, with small random velocities that reflect a relatively quiet history. Their orbits are close to circular, and they stay near the thin plane where gas once cooled and formed them. Accreted stars often move on hotter, tilted, or even counter-rotating paths, because they were born in systems with different angular momentum. When surveys map velocities across Andromeda, coherent groups appear inside the noise, like schools of fish moving against a turbulent current. Those groups are not artistic patterns, they are remnants of disrupted systems still travelling together because phase mixing takes time. The measurements themselves are a technical triumph, because Andromeda is far enough away that individual proper motions are extremely hard to detect. Much of the kinematic work relies on line-of-sight velocities from spectroscopy, where tiny Doppler shifts reveal how fast a star approaches or recedes. Large telescopes collect these spectra one faint red giant at a time, building a map from thousands of points. Even then, the interpretation is delicate because the disk, bulge, and halo overlap in projection. Yet the signatures persist, and the halo refuses to look relaxed. Metallicity adds a second axis of evidence because chemistry tags birthplace in a way that survives long after structure is torn apart. In astronomy, metals mean anything heavier than helium, forged inside stars and dispersed by stellar winds and supernovae. Metal-poor stars tend to form early or in small galaxies with limited enrichment, where gas was not recycled many times. Metal-rich stars usually formed where gas cycled through many generations, steadily accumulating heavier elements. If a stream has a narrow metallicity spread, it likely came from one progenitor with a compact history. If it shows gradients, it may have been a larger dwarf with internal structure, where different regions evolved at different rates. Abundance patterns can sharpen the story even further, because not all metals arrive on the same schedule. Alpha elements, produced largely in core collapse supernovae, rise quickly when star formation is intense and short-lived. Iron builds more slowly when Type Ia supernovae begin to contribute, and that delay acts like a clock. When astronomers can measure ratios like magnesium to iron, they gain leverage on how fast a progenitor formed its stars. The halo is therefore not only a map of where stars are, it is a record of how their birthplaces lived and died. Ages complete the triad, because time separates early assembly from late accretion, and it tells us which wounds are ancient. Old halo stars can be nearly as ancient as the universe, forming when the first generations of galaxies were still small and chaotic. Intermediate age stars in the halo often imply a later merger that brought younger populations outward, where they do not naturally belong. Age dating is difficult at Andromeda's distance, but colour magnitude diagrams and spectroscopy constrain broad epochs, especially near the main sequence turnoff. Even when the uncertainties are large, the distribution of ages can reveal whether a feature formed in one burst or over billions of years. Together, motions, metals, and ages turn the halo into a layered timeline. Deep imaging revealed that Andromeda's halo is not smooth, and the first wide-field surveys made that fact impossible to ignore. It contains tidal streams, shells, and arcs that wrap around the galaxy so faint they can look like scratches on the night. These are the remains of dwarf galaxies pulled apart by tidal forces, their shapes stretched until they become geometry. Their stars do not vanish. They spread along the original orbit like spilled sand, and the orbit itself becomes visible. The patterns persist for billions of years, fading slowly as they mix, and the fading is part of the clue. Tidal streams form when a satellite crosses within the host's tidal radius, where the host's gravity overwhelms the satellite's self-binding. The near side feels stronger gravity than the far side, and the satellite stretches, first subtly and then catastrophically. Stars escape through leading and trailing Lagrange points, forming two elongated tails that peel away in opposite directions. The tails trace the satellite's path through the host halo, and their curvature reflects the orbit's eccentricity and inclination. Their thickness reflects the satellite's internal velocity dispersion, which is tied to its mass and dark matter content. Streams therefore encode both orbit and progenitor mass, even when the progenitor is gone. As the debris spreads, it does not spread evenly, because gravity is not a uniform field and orbits are not perfect circles. Dense clumps can appear where the stream crosses itself in projection, and gaps can form where the debris is stretched thin. Over time, the stream's contrast weakens as phase mixing smooths it out, but the process is slow in the outer halo. A stream is a temporary structure, yet temporary can mean several billion years on galactic timescales. That long persistence is why the halo is such a powerful archive. Shells are a different signature, and they often imply a more radial plunge, where the satellite dove toward the centre and then rebounded outward. When debris moves on elongated orbits, it slows near apocenter and piles up. Because many stars reach their turning point at nearly the same time, that pile-up creates sharp-edged arcs that look like ripples in a pond, except the pond is hundreds of thousands of light-years wide. The effect is called phase wrapping, because different orbital phases overlap in projection, stacking density into a visible edge. In simulations, shells appear as nested structures that expand outward with time, each arc marking another oscillation through the potential. In Andromeda, shells suggest at least one significant accretion on a plunging trajectory. Phase wrapping is not a metaphor. It is orbital mechanics made visible, and it depends on subtle differences in energy. Stars stripped at different times have slightly different energies, so their orbital periods differ by small amounts. They reach turning points at different radii, then crowd together where their radial velocity approaches zero and the density rises. The density contrast is temporary but long-lived, because the halo's orbital periods are immense, and the gravitational potential changes slowly. When astronomers see multiple shell radii, they infer multiple wraps of the same event, like echoes spreading outward. The question becomes not whether a collision happened, but how massive it was and when it struck. The most famous substructure is the giant stellar stream, a vast ribbon extending from Andromeda's disk into the halo, sweeping across the sky in a graceful but unsettling curve. In deep images, it looks like a luminous brushstroke, brighter than most halo features, which means it is either young, massive, or both. Spectroscopy shows it is relatively metal-rich, compared with typical dwarf spheroidals, and that is a crucial constraint. Chemistry like that hints at a substantial progenitor, not a tiny primitive system that formed only a few stars. The stream's geometry and velocity field allow dynamical reconstruction, because the debris still remembers the orbit that created it. Models place its progenitor on an eccentric orbit that passed close to Andromeda's centre, where tidal forces are strongest and stripping is most efficient. That passage would have torn stars away in a burst, producing both a stream and shell-like features as the debris wrapped around. Simulations suggest a progenitor with stellar mass perhaps comparable to a large dwarf or a small spiral, massive enough to enrich its gas and build a complex population. The exact identity remains debated, because multiple scenarios can fit parts of the data. Yet the event was not minor, and the halo structure insists on that conclusion. In these models, the stream is not a single line, but a three-dimensional structure, like a ribbon twisting in space rather than a stripe painted on the sky. Parts of it lie in front of Andromeda, and parts lie behind it, separated by tens of thousands of light-years along our line of sight. Distance measurements using red giant branch stars and variable stars map that depth, turning brightness into geometry. The line-of-sight spread confirms it is debris on a looping orbit, not a static filament or a chance alignment. The stream is therefore a moving fossil, still settling into the halo as gravity continues to sculpt it. The giant stellar stream also constrains Andromeda's dark matter halo, because the orbit depends on the gravitational potential, including its shape and mass profile. A more massive halo bends the stream differently, and a non-spherical halo can twist the debris out of a simple plane. By fitting simulations to the stream's position and velocities, astronomers estimate halo mass and possible triaxiality, narrowing what would otherwise be an invisible guess. The stream becomes a probe of unseen structure, using stars as test particles that trace the field. In a galaxy, the dead can still weigh the unseen, and the measurement is as elegant as it is unsettling. Andromeda's halo contains more than one stream, and that multiplicity matters because it changes the story from a single accident to a repeated habit. A single merger can create complex debris, but many distinct features imply repeated accretion over different times. Surveys like Pandas mapped large areas around Andromeda and found numerous substructures, some stretching like filaments and others curving like broken rings. Some are narrow and cold, suggesting recent disruption of a low dispersion system that had not yet been heated. Others are broad and diffuse, suggesting older events already partially mixed into the background. The halo is a palimpsest, with newer writing layered over older scars, and the older ink is still readable if you know where to look. Globular clusters join this forensic record because they travel with their hosts and survive where looser structures dissolve. These clusters are dense, gravitationally bound swarms of ancient stars, and they can endure tidal stress that would shred a dwarf's outer regions. Some clusters align with streams, implying they arrived inside accreted dwarfs, carried in like cargo. Their metallicities and ages can match the associated debris, strengthening the case for shared origin. Cluster orbits can remain coherent longer than field stars, acting as durable tracers of past infall. In Andromeda, the large cluster population hints at a rich history of ingestion, and it suggests that some meals were substantial. Now shift from debris to the living satellites still orbiting today, because not all evidence is a fossil, and not all victims are gone. Andromeda's satellite system includes M32 and M110, plus dozens of dwarf spheroidals and irregulars scattered through the halo. These companions are not passive ornaments, because they exchange mass and angular momentum with the host, even when they seem distant. Tidal stripping feeds the halo, while gravitational perturbations can warp and heat the disk, leaving signatures that persist. These satellites are both future meals and current agitators, and their present orbits foreshadow their eventual fates. M32 is compact, bright, and puzzling, a small elliptical close to Andromeda's disk, where the tidal field is intense. One idea is that M32 was once larger and lost its outer layers to tidal stripping, a process sometimes called tidal threshing. If true, its present density is the surviving core of a more substantial galaxy, compressed by the loss of its envelope. Its orbit and proximity make it a plausible source of past disturbance, and its very survival implies a history of close interaction. Whether it contributed to specific streams remains uncertain, because multiple progenitors could produce similar debris. Still, its existence signals strong tidal processing, and it reminds us how much can be removed while a core remains. M110 is larger and more diffuse, with its own complex stellar populations that do not fit a single simple burst of formation. It shows evidence of intermediate-age stars and possible recent star formation, which implies it retained gas longer than many dwarf spheroidals. That retention matters, because gas is easier to strip than stars, and its loss can quench future star formation. Its interaction with Andromeda likely strips material and alters its structure over time, gradually reshaping it from the outside in. M110 demonstrates that accretion is not always ancient. It can be ongoing, and it can be slow. The dwarf spheroidals around Andromeda are faint, dark matter dominated and easily disrupted, which makes them both valuable and vulnerable. Their stars are generally metal poor, but each system has a distinct chemical history, reflecting differences in mass, gas retention, and feedback. Some show extended star formation, others quenched early, and that diversity is itself a clue about environment. Their orbits determine their fate because close passages accelerate stripping, while more distant paths allow them to persist longer. As they dissolve, they add low metallicity stars to the outer halo, subtly changing its composition over time. Even when they survive, they are being edited by tides, losing their outskirts first. Some satellites may orbit in a flattened configuration, a possible plane of satellites, and the geometry raises difficult questions. If real, such alignment could reflect group infall, where several dwarfs entered together, already bound or loosely associated. Group infall changes the statistics of accretion, producing correlated debris and shared orbital directions, and it could help explain why some streams appear related. The claim remains debated because selection effects and small number statistics can mimic patterns. Yet the possibility highlights a key point. Accretion can be structured, not random, and the halo may preserve that structure. Satellites also perturb Andromeda's disk, and the disk records those encounters like a sensitive instrument. A thin disk requires calm conditions over long periods, because stars on nearly circular orbits are easily stirred. Minor mergers inject energy into stellar orbits, increasing vertical velocity dispersion, and the consequence is visible thickness. The disk thickens, spiral structure changes, and warps can appear, especially in the outer regions where gravity is weaker. Disk heating is therefore a measure of how often Andromeda was disturbed and how strongly the disturbances struck. A thick disk is not simply a puffed version of the thin disk, it is a distinct population with its own kinematics and chemistry. Thick disk stars are typically older and more metal poor than thin disk stars, and they often show enhanced alpha elements, implying rapid early star formation. Their orbits are less circular and extend farther above the plane, which makes the thick disk look like a faded, elevated layer. In the Milky Way, the thick disk is a major component, and its origin is still debated, ranging from early turbulence to merger heating. In Andromeda, evidence suggests substantial heating, consistent with a more active merger history than our own. The comparison is uncomfortable, because it hints at what repeated impacts can do to a spiral. Minor mergers can also drive radial migration and redistribute angular momentum, meaning stars do not always stay where they were born. Bars and spiral arms can be triggered or strengthened by perturbations, and those patterns can then move stars inward and outward over time. Gas can be funneled inward, feeding central star formation and building the bulge, while outer gas can be torqued into warps. Over time, repeated small impacts can mimic the effects of a larger event, because the energy accumulates. The disk becomes a record of cumulative harassment, written in thickness, asymmetry, and altered rotation. Andromeda's prominent bulge fits this picture, because bulges grow through multiple channels that can overlap in time. Early rapid collapse can build a classical bulge with random stellar motions, producing a hot spheroidal component. Later mergers can add stars and heat the inner disk into a boxier component, blurring the line between bulge and disk. Gas inflow can form a central concentration of younger metal-rich stars, especially if inflow occurs in repeated episodes. The bulge, therefore, does not name one event. It summarizes a long history of stirring. When we look at it, we are seeing the accumulated consequences of instability. Chemical fingerprints in the bulge and halo help separate these channels, because different formation paths leave different abundance signatures. If bulge stars show enhanced alpha elements, they likely formed quickly from core collapse supernova enrichment, before type Ia supernovae could add much iron. If they show more iron relative to alpha elements, star formation lasted longer, allowing delayed enrichment to accumulate. In Andromeda, detailed abundance work is challenging but improving, because individual stars are faint and crowded in the inner regions. Each new spectrum narrows the range of plausible histories, and each ratio acts like a constraint on time. The bulge, like the halo, becomes a chemical archive. The key method is comparative population analysis across substructures, because the power lies in contrasts rather than isolated measurements. Measure metallicity distributions in streams, shells, disk, and bulge, and look for distinctive peaks or tails. Compare age indicators where possible, and compare velocity dispersions and rotation, because dynamics can separate in situ stars from accreted ones. If a stream matches a shell in chemistry and kinematics, they may share a progenitor, and the debris may be different faces of one collision. If a halo component rotates, it may be debris from a disk-like satellite, not a random cloud. The reconstruction is probabilistic, but it is not guesswork, and the uncertainties can be quantified. Simulations provide the second half of the archaeological toolkit, because gravity can be computed even when history cannot be observed directly. In cosmological models, large spirals grow by hierarchical merging, a process predicted by the cold, dark matter framework. Many small accretions build halos, while occasional larger events reshape disks and bulges, sometimes leaving long-lived asymmetries. By matching simulated debris patterns to observed ones, astronomers infer masses, orbits, and times since disruption, narrowing the family of possible pasts. The goal is not a perfect replay, because the initial conditions are never fully known. The goal is a constrained story that fits the evidence without breaking physics. In Andromeda, the emerging picture is of a galaxy that grew aggressively, and the halo is where that aggression is easiest to read. Its halo is structured and metal-rich in places, implying ingestion of substantial satellites that had time to enrich themselves. Its disk shows signs of disturbance, implying repeated minor mergers that injected heat and altered morphology. Its satellite system remains populous, implying the feeding is not finished, and the next disruption may already be in progress. The calm spiral we see is a temporary arrangement, balanced for now between rotation and the slow pull of gravity. This matters for our future, because Andromeda is our approaching partner in collision, and the approach is already measured in precise proper motions. A galaxy shaped by collisions is not stable in the way human intuition expects, because stability in galaxies is often just a pause between interactions. Its outer halo is already full of loosely bound material that can be stripped in an encounter, forming new streams that will bridge the two systems. Its disk has been heated before, and it can be heated again, perhaps into a thicker, more chaotic remnant. The merger with the Milky Way will not be a first trauma, it will be a culmination, and the halo's ghosts are rehearsals. The opening hook returns in a darker form, because the light that looks serene is carrying a warning. Those photons began their journey before civilization, carrying evidence of ancient cannibalism, and they arrive with the same indifferent clarity. The light is old, but the dynamics are current, because gravity continues to operate whether we watch or not. Andromeda is coming, and it comes with a history of consuming smaller neighbours, a history written in streams and shells. That history is the best forecast we have for what it will do to us, and it forces an uncomfortable question. When two giants meet, which parts of each will survive unchanged? Now widen the frame beyond Andromeda's halo, because its environment sets the next chapter. The local group is not empty space with a few islands. It is an interacting system threaded by dark matter and shaped by mutual tides. The Milky Way and Andromeda dominate, but their satellites and dark matter halos overlap in influence, and the boundary between them is not a line. Past collisions built Andromeda's present, and the neighbourhood will shape its future, steering orbits and setting encounter speeds. To understand what awaits, we have to place Andromeda among its nearest companions and follow the gravity that binds them. Transition to the next chapter. The ghosts in Andromeda's halo are not only memories, they are warnings. Subtle at first, then impossible to ignore. The same physics that shredded dwarfs will soon act on two giant disks, and the timescale is short by cosmic standards. The local group is the stage, and the fall has already begun. Now widen the frame beyond Andromeda's halo, because its environment sets the next chapter. The faint smear in our sky is not isolated, and it is not free. It lives inside the local group, a small archipelago of galaxies bound by shared gravity. Close enough to matter, far enough to feel empty. Picture the scene from far outside, where the darkness is not blank but structured. Two bright spirals glow like lanterns, while dozens of dwarfs flicker at the edge of detectability. Between them hangs a thin fog of hot gas and stray stars, almost invisible until you know where to look. The local group contains more than 50 known galaxies, depending on how faint a dwarf you count. New members still appear as surveys deepen, and algorithms learn to recognize low-surface brightness smudges. Many are so diffuse that their stars barely rise above the background, as if gravity is holding together a whisper. Most local group galaxies are small and dim, with low star formation and fragile structure. Some are irregular and gas-rich, still forming stars in bursts when turbulence compresses their clouds. Many are dwarf spheroidals, quenched, metal-poor, and dark matter-dominated, circling like debris around larger hosts. Those dwarfs are not just scenery, because their shapes and orbits are diagnostic. A dwarf with a stretched stellar body hints at tides, and a dwarf with little gas hints at stripping. Even their chemistry matters, since low metallicity preserves a record of early star formation that larger galaxies have overwritten. Two giants dominate this group and set the tone for every smaller orbit. The Milky Way and Andromeda hold most of the stars and most of the mass. Their visible disks are only the inner, luminous parts of much larger gravitational domains, and that mismatch is the first clue that something unseen is in control. Around each disk lies a dark matter halo extending hundreds of thousands of light years. In simulations, those halos are not smooth spheres, but clumpy, layered structures built by mergers. They contain sub-halos, smaller concentrations of dark matter, some of which still carry stars while others remain completely dark. Those halos matter more than the starlight, because they define the true boundary of influence. A halo is not a decorative envelope, and it is not optional. It is the main reservoir of mass that shapes satellite orbits, tidal stripping, and long-term stability. In the local group, halos overlap in reach even when disks remain far apart. The overlap is subtle at first, just a shared pull on distant dwarfs and gas, but it grows as the giants approach. When you look at the sky, you see two galaxies. When gravity looks back, it sees two interpenetrating potentials. This is where the central question gains pressure. What is Andromeda truly like, if its future is not chosen by stars but by mass? What will it mean for life and astronomy if the local group is already steering our sky toward collision, slowly, relentlessly, and without spectacle until the final acts? The local group is often pictured as a loose neighbourhood, but it behaves more like a tent system. Gravity does not negotiate, and it does not forget. It pulls on everything at once, and the response can take billions of years to become obvious. The conspiracy is not intention, and it is not malice. The conspiracy is inevitability, an outcome written into initial conditions, then edited by every encounter since. If that sounds abstract, the evidence begins with a simple number measured from light. Start with the simplest measurement, because it is the first clue that Andromeda is coming. Astronomers measure Andromeda's radial velocity, the component of motion along our line of sight. The value is about -300 kilometers per second relative to the Sun, and the sign is the headline. The negative sign means the light is blue shifted and Andromeda is approaching. In a spectrum, that approach is not a metaphor but a displacement. Familiar absorption features, calcium lines, hydrogen lines, and other atomic fingerprints slide towards shorter wavelengths, as if the galaxy is pulling them forward. The method is old physics applied to a distant target. Spectral lines act like rulers stamped into starlight, with known rest wavelengths measured in laboratories. If the galaxy moves toward us, those lines shift to shorter wavelengths. If it moves away, they shift redward. The amount of shift gives the speed, and the relationship is governed by the Doppler effect. At a few hundred kilometers per second, the shift is small but measurable with modern spectrographs. The trick is precision, because you are comparing tiny displacements to reference lamps and calibration standards. Radial velocity is persuasive because it is direct and repeatable. It does not require us to watch the galaxy drift across the sky, and it does not depend on a model of its shape. It only requires a spectrum and careful calibration against local motion, which is where the subtlety hides. Even then, the measurement must correct for Earth's orbit and the Sun's path through the Milky Way. Our planet adds a seasonal wobble, and the Sun adds a steady motion around the galactic centre. Astronomers subtract those motions to isolate Andromeda's approach relative to the Milky Way itself. But radial velocity alone does not give the full trajectory. A galaxy can approach in the line of sight while also sliding sideways, and that sideways component determines whether the encounter is a direct hit or a glancing blow. That sideways component is the transverse velocity, and it is far harder to measure at 2.5 million light-years. The challenge is not conceptual because the geometry is simple. The challenge is that the angle is tiny, and tiny angles are where measurement becomes an art. At Andromeda's distance, even a substantial sideways speed translates into a motion smaller than the thickness of a human hair seen from kilometers away. Proper motion is the apparent angular shift of an object across the sky over time. For nearby stars, proper motion can be large enough to see over years, and it was once a key clue that stars are not fixed. For Andromeda, the expected drift is measured in microarc seconds per year. That is like watching a coin move on the moon from Earth, and then insisting you can measure the direction. The sky becomes a ruler with marks too fine to see, so astronomers build a ruler out of time. They return to the same fields again and again, letting years become their lever arm. This is why the local group story waited for modern instruments. The Hubble Space Telescope provided a long, stable baseline in space, free from atmospheric blur and nightly distortion. By tracking fields of stars and background galaxies, Hubble constrained Andromeda's proper motion against objects so distant they barely move. The result suggested a small transverse speed, consistent with a near head-on approach. That conclusion is not a single measurement but a statistical one, assembled from multiple fields and careful control of systematics. The uncertainty bars still matter, because the difference between small and moderate decides the choreography. Gaia changed the context by mapping the Milky Way with extreme astrometric precision. Gaia does not directly measure Andromeda's stars with the same ease, because they are faint and crowded at its distance. Yet Gaia improves the reference frame, the calibration of our own motion, and the biases that limit other measurements. The Gaia era tightens the net around the local group's true dynamics. It refines the solar motion, improves distances to calibrate to stars, and stabilizes the celestial coordinate grid itself. When you try to measure microarc seconds, even the definition of still becomes part of the experiment. Even with these tools, the uncertainty remains important, because small angles become large consequences. A modest transverse velocity can turn a direct collision into a near miss, or at least a longer, looping first passage. It can change the timing of first passage by hundreds of millions of years. It can also change how much gas is shocked, and how violent the starbursts become. Gas is collisional, so it can slam into gas and heat up, while stars mostly pass through. The geometry determines whether the gas disks interpenetrate early, or only after repeated tidal stirring. So the documentary must hold two truths at once. The approach is real, because the radial velocity is strongly negative and has been confirmed for decades. The exact geometry is still being refined, because proper motion is difficult at this distance. The future is constrained, not perfectly predicted. Now connect motion to mass, because gravity is the engine behind every orbit we have described. If Andromeda and the Milky Way were not bound, cosmic expansion could separate them over time, and their approach would be a temporary illusion. If they are bound, their mutual gravity must overcome that tendency. The question becomes quantitative, and it becomes unavoidable. How much mass is required to keep the local group together, despite the universe's overall expansion? In other words, how heavy must the invisible stage be to hold the actors in place? Introduce the timing argument, because it is one of the simplest and most unsettling in cosmology. It emerged in the 20th century as astronomers began to treat galaxies as dynamical systems, not static pictures. The idea is almost audacious. Use the age of the universe as a stopwatch. Assume the Milky Way and Andromeda began near each other after the Big Bang. Assume they moved apart with the general expansion, then slowed, turned around, and began to fall back together. Use the age of the universe, about 13.8 billion years, as the clock for that full arc, with the current separation of about 780 kiloparsecs and the observed approach speed. The timing argument estimates the total mass needed. The answer is large, on the order of several trillion solar masses for the pair. The visible stars and gas do not come close to that number. The missing mass points again to dark matter, and it does so in a way that feels almost personal. You can count Andromeda's stars, estimate its gas, and still come up short by a factor that cannot be ignored. The local group behaves as if it is embedded in something massive and unseen. The timing argument is not a perfect model, and it is not meant to be. It treats the system as an idealized two-body problem in an expanding universe, like a simplified sketch of a complicated machine. It ignores some complications from other group members and the detailed growth of halos, yet its strength is that it uses only a few observables in a universal timescale. It does not require you to know every satellite orbit or every past merger. It asks a blunt question: how much gravity is needed? And the universe answers with a number too large for ordinary matter. The conclusion is robust even when the details shift. The local group must be massive, and most of that mass must be dark. The Milky Way and Andromeda are not just bright disks drifting in empty space. They are the visible cores of much larger gravitational structures. This changes how we should picture the local group. The group is not a set of islands separated by void, even if it looks that way in photographs. It is a web of overlapping potentials, where satellites move inside invisible wells, and where between is not the same as empty. Dwarfs are not merely companions, and they are not merely victims. They are test particles tracing the shape and depth of dark matter halos, and their tidal streams act like ink in water. When a dwarf is shredded, its stars draw arcs that reveal the gravitational field that tore it apart. Dark matter halos also explain why small galaxies survive as long as they do, and why they eventually fail. A dwarf can be held together by its own dark matter even when its stars are sparse, like a loose swarm bound by an unseen glue. But when it enters a larger halo, tides strip its dark matter first, the stars follow later, and the debris becomes streams, shells, and diffuse halos. Those structures persist for billions of years, slowly phase, mixing into a smoother background. When we map them, we are reading a crime scene where the culprit is gravity and the weapon is time. That story connects directly to earlier chapters. Andromeda's halo is a confession because it is a record of tidal stripping inside a massive potential. The local group provides the larger stage where that stripping is common, not exceptional. The same physics that shredded dwarves will soon act on two giants. Now introduce the third major player, because three bodies change everything. The Triangulum Galaxy, M33, is smaller than the Milky Way and Andromeda, but it is not negligible. It is a spiral with active star formation, bright nebulae, and a significant dark matter halo. It orbits within Andromeda's sphere of influence, and it may already be dynamically entangled. Even from Earth, M33 can be imagined as a companion light near Andromeda, close enough in the sky to suggest a relationship. In 3 dimensions, that relationship becomes a gravitational negotiation that never truly ends. M33 is the wild card because its orbit is uncertain and its future is conditional. If it has had close passages with Andromeda, it could have helped disturb Andromeda's disk, bending it and stirring its outer gas. If it will have a close passage in the future, it could be stripped or captured more tightly. In some scenarios, it collides with Andromeda before the Milky Way arrives. That would preheat the system, adding tidal debris, thickening halos, and redistributing angular momentum before the main event begins. The local group then becomes less like a duel and more like a chain reaction. A three-body system is unstable in the long run, even when it looks calm today. Energy and angular momentum can be exchanged through repeated interactions, and those exchanges can be surprisingly efficient. Small differences in initial conditions can lead to different outcomes over billions of years. The local group is therefore not only a merger story, it is a dynamical drama with branching paths, where uncertainty is not ignorance but a measurable range. When we simulate the future, we do not get one film, we get a family of films, all plausible, all shaped by the same laws. Explain why M33 matters for the Milky Way and Andromeda merger outcome. If M33 falls into Andromeda first, it can add mass to the inner halo and change the distribution of angular momentum. It can torque Andromeda's disk and alter its orientation before first passage with the Milky Way. It can also seed additional tidal debris that will later be pulled into the combined remnant. Those extra streams are not cosmetic because streams carry orbital memory. They can influence how gas settles, how stars are heated, and how the final merged galaxy, often called Milkomeda in popular accounts, will look. In other scenarios, M33 is flung outward during the Milky Way-Andromeda interaction. A close three-body encounter can act like a gravitational slingshot, transferring orbital energy from the giants to the smaller galaxy. The smaller galaxy can gain energy and move to a wider orbit, or even escape the local group. The details depend on the transverse velocities and the timing of close approaches. A difference of a few tens of kilometers per second, sustained over billions of years, can decide whether M33 becomes part of the remnant or a wandering exile. That sensitivity is the signature of nonlinear dynamics, even in a quiet sky. This is where the documentary's mysterious tone belongs, because the future is both constrained and unknowable in detail. Gravity is deterministic, but our knowledge of initial conditions is limited by distance, crowding, and instrument systematics. We can measure velocities and distances, but not perfectly. The local group is a system where small uncertainties can echo into large differences. It invites a thought-provoking question. If the laws are exact but the measurements are not, how close can we come to predicting a cosmic future? The answer is not despair. It is humility paired with rigor. Return to the evidence that the Milky Way and Andromeda are bound, because that is the spine of the chapter. The negative radial velocity is one line of evidence, and it is the most intuitive. The timing argument is another, requiring a massive bound pair dominated by dark matter. The satellite distributions and halo masses inferred from rotation curves support the same picture. Rotation curves, flat where they should fall, imply extended mass far beyond the visible disks. When multiple methods converge, the conspiracy begins to look less like speculation and more like a measured structure. Add a crucial clarification, because popular images often mislead. The Milky Way and Andromeda are not rushing toward each other like cars on a highway. Their relative speed is large by human standards, but small on cosmic scales, where galaxies routinely orbit for billions of years. The approach is slow, and the merger will unfold over billions of years. The inevitability comes from patience, not violence, and that patience is what makes it eerie. The night sky can look unchanged for a lifetime while the gravitational countdown continues in silence. Yet slow does not mean gentle. When halos overlap more deeply, tides will grow stronger and begin reshaping both galaxies, even before the disks touch. Gas will respond first because it can shock and cool, and because it can radiate away energy as light. Star formation will flare in compressed regions, and central black holes may be fed by inflows. Those inflows can be driven by gravitational torques that remove angular momentum from gas, funneling it inward. The visible fireworks will be delayed, but the gravitational commitment is already in place. Now place the local group in a slightly wider context, because isolation is part of the reason this merger happens. The local group sits on the outskirts of the Virgo supercluster environment, in a region without a nearby massive cluster to dominate the dynamics. There is no external giant pulling the two spirals apart. The dominant forces are internal, set by the group's own mass and the expansion background. In that sense, the local group is a laboratory where gravity can play out with fewer interruptions. It is not perfectly isolated, but it is isolated enough for the long arc of a merger to proceed. The local group also has its own centre of mass, a barycenter that lies between the Milky Way and Andromeda. Smaller galaxies orbit that combine potential, not leave the disk alone, and their motions can reveal where the barycenter sits. In a map you would not see it, but in velocities you can feel it. Some dwarfs are clearly Milky Way satellites, bound deep inside our halo. Some are clearly Andromeda satellites, arranged in swarms and planes that still puzzle dynamicists. Others sit in the ambiguous region where the group potential dominates, and where membership is not a label but a probability. This ambiguity is not a footnote, because it reveals the scale of the dark matter stage. The boundary between the Milky Way and Andromeda is not a line in space. It is a gradient in potential, shaped by two halos and their growth history. Where that gradient lies affects which dwarfs are captured, stripped, or exchanged. A dwarf can be tugged one way for billions of years, then slowly handed off as the barycenter shifts. The local group becomes a place where even ownership is dynamical, and where the past is written into present-day orbits. Measuring those dwarf motions is difficult, but it is improving. Line-of-sight velocities are easier than proper motions, and they already show coherent satellite systems. Proper motion measurements for some local group dwarfs are emerging, using Hubble and Gaia anchored frames. Each new orbit helps map the group's mass distribution, and each orbit is a constraint on the invisible. When you know where a dwarf has been, you learn what pulled it. In that way, the smallest galaxies become instruments, delicate probes of a force we cannot see directly. Now tighten the narrative back to the opening hook, because the ancient glow is also a moving target. The photons that left Andromeda 2.5 million years ago carry a snapshot of its past, a picture taken before humans existed. The gravity that brings Andromeda toward us is acting now, in our present. We watch an old image of a galaxy that is already closer than the light suggests. The paradox is only apparent, but it is emotionally real. The universe makes us witnesses to history, while we try to forecast a future that has not yet arrived. That time delay creates a documentary tension that should not be softened. We infer the future from data that is already ancient, and we do it with instruments that must be calibrated against our own motion. We measure motion with exquisite care, then project it forward across timescales that dwarf civilization. The local group becomes a lesson in humility, but also in method. We can know the direction of fate before we can know its details, and that is often how science works. First comes the sign of the effect, then comes the slow narrowing of uncertainty. Summarize the key evidence in one coherent chain. Andromeda's spectrum is blue-shifted, giving a strong approach speed along the line of sight. Proper motion constraints suggest the sideways motion is not large enough to avoid interaction, even if it can reshape the encounter. The timing argument demands a massive bound local group dominated by dark matter. The presence of M33 adds complexity, and it adds alternative pathways, but it does not remove the gravitational commitment. The actors may improvise, yet the stage still tilts toward the same ending. Now make the chapter's core claim explicit, because it is the hinge into the next topic. The local group is a gravitational conspiracy, because the visible galaxies are only the actors. The stage is an invisible structure of dark matter that sets the script. If gravity is the script, dark matter is the stage, and the stage is already tilted toward merger. That metaphor is not poetic excess, because the numbers demand it. Without dark matter, the local group would not hold together long enough for this slow collision to be inevitable. Transition forward with a sharper question, because the next chapter must deepen the mystery rather than resolve it. We have measured approach, inferred mass, and mapped a three-body tension. We still have not seen the main component that makes the numbers work. The next step is to follow the missing mass, and ask what kind of invisible architecture can bind a group for billions of years. Is it smooth or clumpy, calm or turbulent, ancient or still growing? And if it is everywhere, why does it reveal itself only through motion? If Andromeda is a time-delayed message, then the local group is the envelope that carries it. It tells us that galaxies are not solitary, and that their futures are written in shared gravity. The collision is not an accident in empty space. It is the natural outcome of a bound system evolving on cosmic time, where the most important structures are the ones we cannot photograph. In the darkness between galaxies, the conspiracy continues, quiet, patient, and already in progress. The night sky tempts us to trust what shines, but gravity trusts what weighs. Andromeda's ancient light is a moving postcard, yet the force steering it is mostly unseen. If gravity is the script, dark matter is the stage, and the stage is already tilted toward merger. Begin with the problem that first broke the neat picture of galaxies as luminous islands. Early photographs made spirals look self-contained, bright pinwheels floating in blackness, their arms crisp where starlight was dense. In a simple system, orbital speed should drop with distance, because most mass sits near the center. Planets in our solar system obey that rule, and their speeds fall as the sun's pull weakens with radius. A spiral galaxy should behave similarly if starlight traces most of its mass, and if the outskirts are truly thin. That expectation is not just intuition. It is the mathematics of gravity written in circular motion. For an object in a stable orbit, speed depends on the mass enclosed within that radius. If the enclosed mass stops growing, the speed must decline, and the curve should fall like a fading echo. The bright disk in that tidy picture is the whole story, an island of stars whose light also marks its weight. But when astronomers measured rotation in spirals, the outer parts refused to slow down. Gas clouds and stars far from the bright disk moved too fast to be held by visible matter alone. The rotation curve stayed flat, meaning velocity remained high even where the light thinned out. That flatness implied extra mass spread far beyond the luminous edge, as though the galaxy's true body extended into darkness. Historically, the shock arrived in stages, and it arrived with instruments rather than arguments. In the mid-20th century, radio astronomy matured, and neutral hydrogen became a tracer of the outskirts. Optical telescopes could see the bright disk, but radio dishes could hear the faint cold gas beyond it. When those measurements were plotted, the curve did not fall away politely. It held steady, stubbornly, like a hand refusing to let go. Explain how rotation curves are actually measured, because the mechanism is simple and decisive. Spectra reveal Doppler shifts, with one side of a disk approaching and the other receding. The lines are not just pretty fingerprints, they are clocks that tick faster or slower depending on motion. In radio, the 21-centimeter line of neutral hydrogen maps motion well beyond optical starlight, tracing diffuse gas where stars are scarce. In optical, emission lines from ionized gas and absorption lines from stars extend the map inward, closer to the bulge. Combine those velocities with distance from the center, and the curve becomes a mass test. Visually, it is a clean geometry, almost too clean for such a profound conclusion. One side of a galaxy shifts slightly toward blue, the other toward red, and the split encodes rotation. Astronomers correct for tilt, because a disk seen edge-on exaggerates speed while a face-on disk hides it. They also correct for distance, because a kiloparsec on the sky is not a kiloparsec in space without a scale. After those corrections, the curve is a verdict delivered in kilometers per second. The mismatch is not subtle when you do the arithmetic. If only stars and gas mattered, the inferred mass would level off near the bright disk. Instead, the enclosed mass keeps rising with radius, as if the galaxy sits inside a vast invisible reservoir. The simplest interpretation is a dark matter halo, massive, extended, and dominant. In that picture, the bright spiral is only the inner tracer of a much larger structure, like a lantern hung inside a cathedral. And the curve's flatness has a physical meaning that is easy to say in plain language. If speed stays roughly constant as you go outward, then mass must keep accumulating with radius. The outskirts are not empty, they are heavy. Gravity, in other words, is responding to something that does not glow. Bring the focus back to Andromeda, because our central question depends on its true mass. Andromeda's disk is larger than the Milky Way's, but size alone does not decide the future. What matters is the total gravitational potential, especially in the outer halo where the encounter begins. Rotation data and satellite motions suggest a halo reaching hundreds of thousands of light years, fading gradually rather than ending cleanly. The coming collision is therefore a halo event long before it becomes a disk event. Imagine the visual. Andromeda's bright oval, familiar in binoculars, surrounded by an enormous transparent sphere. That sphere is not a special effect. It is the dominant mass budget. If you could see it, the galaxy would look less like a disk and more like a ghostly planet, with a thin, luminous atmosphere. Our own galaxy would carry a similar shroud, and the two shrouds would be the first to meet. Rotation curves alone could still be challenged by hidden, ordinary matter, like faint stars or cold gas. Astronomers did consider that possibility, because science prefers mundane explanations before exotic ones. Could there be swarms of dim red dwarfs, or clouds of molecular hydrogen too cold to radiate? Yet those ideas run into limits from nucleosynthesis, from star counts, and from the way ordinary matter interacts and cools. That is where a second line of evidence enters, and it does not rely on the galaxy's own light. Gravity bends light from background sources, turning space into a lens. The deflection depends on total mass, not on whether that mass glows. Lensing lets us weigh the invisible directly through geometry, using the universe itself as an optical bench. It is a measurement that feels almost unfair, nature doing the experiment for us. Introduce the principle without slowing the narrative. In general relativity, mass and energy curve space-time, and light follows the curved paths. A foreground galaxy can distort the shapes of background galaxies into arcs, smears, and subtle alignments. Strong lensing produces dramatic arcs when alignment is tight and mass is dense, sometimes even multiple images of the same source. Weak lensing produces statistical shape distortions across many background galaxies, a faint pattern that emerges only after careful averaging. Both effects map mass distributions that starlight cannot explain. For the viewer, strong lensing is the cinematic version. Bright crescents wrapped around a hidden center. Weak lensing is quieter, more like a whisper in a crowd, but it is powerful because it works almost everywhere. It treats every distant galaxy as a test particle, and every foreground mass as a sculptor of paths. When the shapes line up more than chance allows, the lens has revealed itself. Connect lensing to halos because that is the mechanism we need for the merger story. Lensing measurements around galaxies and clusters show mass extending well beyond visible boundaries. The inferred profiles match the idea of halos with dense centers and diffuse outskirts, falling with radius but never dropping to zero. They also reveal that most mass is not in disks or bulges, but in broad envelopes. The universe behaves as if dark matter is the main scaffolding for galaxy formation, and ordinary matter is the luminous decoration. There is also a historical resonance here, because lensing was once a rare curiosity. Einstein himself treated it as a clever consequence, not a routine tool. Now it is a survey technique, applied across billions of light years, and it keeps returning the same message. The mass is there even when the light is not. Clarify what lensing does and does not tell us in the local group context. The Milky Way and Andromeda are too close and too spread out for the most dramatic lensing signatures. Their mass is real, but their lensing imprint on background galaxies is subtle and hard to isolate against local structure. Yet lensing across the broader universe validates the same halo concept that rotation curves imply locally. It supports the idea that halos are real structures, not bookkeeping tricks. That matters because our merger predictions assume halo physics is universal. Now move from evidence to architecture, because the collision's shape depends on halo structure. Halos are not sharp shells with clean edges, and they are not static spheres. In simulations, they are layered, clumpy, and sometimes triaxial, shaped by mergers and ongoing accretion. Their density falls with radius, but their influence persists far into intergalactic space. The boundary is a gradient where inside becomes a matter of definition, and definitions depend on how you choose to measure. This is where Chapter 4's local group frame tightens into a mechanism. Two giant halos can interact while their bright disks remain widely separated. Their outer regions can overlap, exchanging tidal influence and perturbing satellite orbits. Some models suggest the Milky Way and Andromeda halos may already touch at the fringes, where densities are low but volumes are vast. If so, the merger has begun in the only way gravity knows, through shared potential. Explain what overlap means in practical terms, because it is not a collision of particles. Dark matter is effectively collisionless, so halos interpenetrate rather than shock. Overlap means the combined gravitational field changes the trajectories of satellites, gas clouds, and the halos themselves. It also means the barycenter of the local group is embedded in a continuous mass distribution. The space between galaxies is not empty in a dynamical sense, even when it looks empty to the eye. Picture that in motion. Two invisible clouds passing through each other, their particles rarely meeting, yet their gravity constantly negotiating. Streams of stars, like the ones we traced earlier, feel those negotiations as subtle tugs. Dwarf galaxies on the outskirts can have their orbits twisted, their paths bent into new planes. Even the timing of a future close pass can change, not because anything touched, but because everything pulled. Bring in halo sizes and mass estimates, because uncertainty here becomes uncertainty in fate. Andromeda's total mass is often quoted around 1 to 2 trillion solar masses, but ranges remain wide. The Milky Way's mass is similarly uncertain, and the ratio matters for the remnant's centre. Different tracers give different answers, including satellite velocities, globular cluster motions, and stream fitting. The giant stellar stream from Chapter 3 becomes a key probe of Andromeda's potential, because it is long, coherent, and sensitive to the halo's shape. Those mass estimates are not just numbers on a chart, they decide how deep the gravitational well is. A heavier halo strengthens dynamical friction, shortens timescales, and pulls harder on companions. A lighter halo weakens the braking, allowing wider swings and longer delays. When we say a few billion years, we're really saying a few billion years given a halo we cannot see. Return to that earlier anchor, because this chapter must resolve it into the merger story. Stream orbits respond to the halo's mass profile and shape, including possible triaxiality. If the halo is more massive, the stream's path bends differently, and its debris wraps on different timescales. If the halo is elongated, the stream can precess and thicken in characteristic ways. Every fit is a constraint on the invisible scaffold that will steer the Milky Way encounter, and every mismatch is a clue about what we assumed. There is a quiet elegance to this method, because it turns wreckage into a ruler. A disrupted satellite leaves behind a trail, and that trail is a record of gravity over time. The stream's width hints at heating and perturbations, while its curvature reveals the underlying potential. We are reading Andromeda's autobiography, but the ink is written in orbits. Now introduce the process that turns a bound approach into an inevitable merger. The key is dynamical friction, an effect that sounds like drag but arises from gravity alone. A massive object moving through a sea of particles pulls them into an overdense wake. That wake lags behind and exerts a gravitational pull backward. Orbital energy and angular momentum are transferred to the surrounding halo, and the transfer is cumulative. State the consequence clearly, because it is the invisible braking system of galaxy mergers. As the Milky Way and Andromeda pass, their halos raise, wakes in each other's dark matter. Those wakes drain orbital energy, shrinking the orbit after each close approach. The galaxies do not simply swing past and escape, because the halo absorbs the motion. Dynamical friction turns repeated encounters into a tightening spiral, even when the first pass is fast and wide. This is a subtle point that deserves one more visual beat. The wake is not a solid thing. It is a statistical crowding of particles, a gravitational echo trailing behind the moving mass. The moving galaxy climbs its own gravitational hill because the wake pulls backward. Over billions of years, that backward pull matters more than a single dramatic moment. Connect this to why halos matter more than disks in the early phases. The disks contain much less mass than the halos, so they are not the main sink for orbital energy. The halo is the reservoir that can accept energy without immediately radiating it away, because collisionless particles do not heat and glow like gas. As the orbit decays, tidal forces grow, and the visible structures begin to respond. The merger is therefore driven by what we cannot see, then revealed by what we can. Add the local group complication, because Chapter 4 introduced M33 as a wildcard. A third halo changes the exchange of energy and angular momentum. If M33 has already interacted strongly with Andromeda, it may have altered Andromeda's halo profile and orientation. If it interacts during the Milky Way approach, it can be captured, stripped, or flung outward. These branches depend on halo masses and transverse velocities, not on starlight. On screen, that complexity can look like a dance with three partners, each tugging at the other's sleeves. A small change in M33's path can shift the timing of a close pass, or tilt the plane of the encounter. The luminous disks may look stable, but the invisible halos are constantly exchanging momentum. The choreography is written in mass, and mass is mostly dark. Now address competing models, because the documentary must hold mystery alongside mechanism. Dark matter is the dominant framework, but details remain contested and measurable. Halo mass estimates depend on tracer selection, distance uncertainties, and assumptions about equilibrium. Velocity anisotropy in satellite populations can bias inferred masses upward or downward. Even the halo's outer slope affects how strongly dynamical friction acts over time, because friction depends on how much material the galaxy moves through. Explain anisotropy in one dense beat, because it is a major uncertainty lever. If satellite orbits are mostly radial, line-of-sight velocities can look large without implying a huge mass. If orbits are mostly tangential, the same data can imply a deeper potential. Without full three-dimensional motions for many tracers, models must marginalize over plausible anisotropies. That uncertainty propagates directly into merger timing, and it widens the forecast window. Include the role of proper motion constraints from Chapter 4, because geometry shapes the choreography. A small transverse velocity implies a near head-on first passage, with strong tides and efficient friction. A larger transverse velocity implies a more glancing encounter, possibly delaying coalescence. The difference can be hundreds of millions of years, sometimes more, depending on halo mass and on how extended the outskirts are. The future is constrained, but it is not a single calendar date. Acknowledge that even the nature of dark matter can alter small-scale structure, and therefore the merger's fine details. Cold dark matter predicts many subhalos, which can perturb streams and heat disks. Warmer or self-interacting models can smooth inner densities and reduce substructure, changing how centrally concentrated the halo becomes. Those changes can shift how quickly wakes form and how strongly friction acts. The broad outcome remains a merger, but the pathway can vary, and the sky's transformation may arrive with different rhythms. Now tie the evidence back to the central question, because this chapter is a hinge. What is Andromeda truly like if most of it is invisible, and if that invisibility decides our future sky? The galaxy we see is an illuminated skin stretched over a dark framework. Its past mergers, traced by streams and shells, occurred inside that framework. Its future collision with us will be negotiated by the same unseen mass, long before any starfield looks disturbed. This is the unsettling observation, and it is also the profound one. We evolved under a sky that looks stable, and we built myths around the lights we could name. Yet the dominant architecture of our cosmic neighborhood is not the lights, it is the weight. If you could dim every star and keep only gravity, the local group would still be there, and its fate would be the same. Make the mechanism personal to the local group because the documentary's hook is intimate. The faint smear of Andromeda looks unchanged across human history, yet its halo is already engaged with ours. The approach speed is measured in spectra, but the commitment is enforced by dark matter. The collision is not a sudden event, but a long gravitational capture. The night sky is quiet because the main actor does not shine, and because the timescale is measured in eons. Summarize the chain of reasoning in one compressed sequence. Rotation curves show outer stars orbit too fast for visible mass, implying extended halos. Lensing across the universe confirms mass distributions that exceed starlight and match halo profiles. Halo sizes make overlap plausible, meaning interaction begins before disks touch. Dynamical friction in massive halos drains orbital energy and makes escape unlikely. Uncertainties in mass and anisotropy shift timelines, but not the direction of fate. Now pivot toward the next chapter, because the physics must become a forecast. With the invisible scaffold established, we can run the clock forward with simulations and constrained initial conditions. We can ask how many close passages occur, how tides reshape disks, and where the remnant stars end up. We can also ask what happens to gas, star formation, and the view from any surviving planetary systems. The next step is not more evidence, but the unfolding choreography, transition. With the stage finally visible through its effects, the story can move from mystery to motion. We have weighed the darkness, and it weighs on our future. Now we let time advance, and we watch what an inevitable collision actually looks like. Begin the future timeline because the approach becomes an event only in deep time, when continents drift, oceans cycle, and species rise and vanish without noticing the sky's slow change. The Milky Way and Andromeda keep falling together for billions of years, while human history remains a thin layer on the clock. In that span, Even the sun's steady brightening matters as its luminosity creeps upward and nudges climates toward new equilibria. Yet the galaxies keep their appointment, silent, inevitable, and written into motion. The central question tightens as the distance shrinks and the sky begins to change, because a nearby galaxy is no longer an object but a landscape. What is Andromeda truly like when it stops being a smudge and becomes an environment, an extended system of stars, dust, gas, and dark matter that can reach into ours? It is not a flat picture, but a layered structure with a bright bulge, a rotating disk, and a halo that extends far beyond the visible light. Call back the opening hook, because its ancient photons now foreshadow a nearer truth that feels almost personal. The light we see is old, but the gravity that moves it is present, acting now across a space that is steadily collapsing. Every moment, the gravitational field updates instantly in the language of physics, while the visible image lags behind like a memory. That mismatch is eerie. Our eyes report the past, while our orbits respond to the present. Set the scale with numbers that feel slow and unavoidable, because the mind needs a ruler for billion-year stories. First close passage is expected roughly 4 billion years from now, with uncertainty that still matters. That estimate comes from combining distance, radial velocity, and proper motion, measurements refined by space observatories, and careful statistical modelling. The radial approach is measured through Doppler shifts in spectral lines, while the sideways drift is inferred from minute changes in position against far background sources. Define what we mean by collision, because the word misleads and invites the wrong mental picture. Galaxies collide by gravitational interpenetration, not by stars smashing together like stones. Their structures overlap, their potentials distort, and their contents are redistributed, even if individual stars rarely touch. The real impact is a collision of gravitational fields, where the shape of spacetime's pull is rewritten over millions of years. The galaxy is mostly empty space, even where it looks crowded in photographs of spiral arms. Typical stellar separations are measured in light years, while stars themselves are measured in millions of kilometers. If the solar system was scaled to a peppercorn, the nearest star would still be kilometers away. Space is that empty. Even dense star clusters are airy by everyday standards, and the disk is more like a luminous fog than a solid city. So when the disks overlap, most stars simply pass by with their trajectories gently bent, like a school of fish slipping through another in deep water. The catastrophe is not direct impact, it is tidal distortion and the rearrangement of orbits. Gravity does not need contact to do damage, it only needs asymmetry and time. Over repeated passes, those small deflections accumulate, and the disk's orderly rotation begins to fray. Yet galaxies absolutely do collide, because their gravity cannot pass through unchanged when two massive systems overlap. Their halos overlap first, and dynamical friction keeps draining orbital energy into the dark matter sea. That friction is not rubbing surfaces, but a gravitational wake, an overdensity that tugs backward and steals momentum. In simulations, the wake looks like a trailing swell in an invisible ocean, and it deepens as the encounter tightens. Introduce first pericenter as the chapter's hinge, because everything we see later is set by this initial close approach. The encounter is a closest approach, not an immediate merger, and it sets the rhythm of everything after. Like two dancers who spin past each other before returning, the first pass establishes the tempo of repeated encounters. It also sets the first major transfer of angular momentum, which decides how quickly the pair can be captured into a tighter embrace. Give the predicted distance range without pretending it is settled, because the future is constrained, not scripted. Many simulations place first pericenter around tens of kiloparsecs, often quoted near 20 to 50 kiloparsecs. In more familiar terms, that is on the order of tens to hundreds of thousands of light years, close on galactic scales, still vast on human ones. Even at that distance, the outer halos are deeply entangled, and the disks feel the pull like a slow tide. Other plausible runs allow a wider swing closer to 60 or even 100 kiloparsecs, and that difference changes what the sky looks like. The spread comes from proper motion uncertainty, and from uncertain halo masses and profiles. A small change in sideways velocity today becomes a large difference in geometry billions of years later. It is a reminder that prediction here is not prophecy, but probability mapped onto a cosmic stage. Connect that spread to Chapter 4's measurement problem, because the viewer has already met the limits of our instruments. A small transverse velocity favours a near head-on passage, while a larger sideways component yields a glancing approach. Proper motion is measured in microarcseconds per year, angles so tiny they test the stability of telescopes and the patience of astronomers. Historically, even proving that galaxies were separate island universes took a revolution in measurement, and now we chase motions smaller than a coin seen from the moon. Connect it to Chapter 5's invisible scaffold, because the halos are the main actors even when they cannot be filmed. A heavier halo increases dynamical friction and pulls the first pass inward, while a lighter halo allows a looser first swing. Halo shape matters too, because a triaxial potential can twist trajectories and change where tidal features emerge. Substructure matters as well. Clumps of dark matter can tug on streams and subtly roughen what would otherwise look smooth. Acknowledge the branching films without losing momentum, because multiple futures can share the same ending. The exact choreography varies, but the shared outcome remains repeated encounters that tighten toward final coalescence. In every credible run, the two great spirals do not simply wave and drift apart. Their mutual gravity keeps calling them back. The question is not whether the first pass happens, but how dramatic its scars will be. Now describe the first visible signatures, because gravity writes on structure long before the centers come near. As the galaxies approach, tidal forces stretch disks, warp outer gas, and begin lifting stars into long arcs. The first hints may be subtle, an outer ripple, a fainter symmetry, yet they are the opening lines of a much larger script. In deep imaging, the outskirts would look disturbed first, like a calm pond showing rings before the splash is seen. Tides are differential gravity, and they scale with distance in a ruthless way that punishes closeness. The near side is pulled harder than the far side, and the disk cannot stay symmetric. In plain terms, the galaxy is being pulled unevenly, and that uneven pull becomes a sculptor. The same principle raises ocean tides on Earth, but here the water is stars and gas, and the shoreline is tens of thousands of light years wide. Explain tidal tails in one clean mechanism, because the beauty has a simple cause. Material on the far side can be flung outward into a tail, while material on the near side can be drawn into a bridge. The process depends on orbital phase and rotation direction, so the tails can be long and clean in one geometry, shorter and messy in another. Some tails remain bound and later rein back in, while others drift outward as faint, long-lived signatures of the encounter. Those tails are not decoration, because they move angular momentum around like levers in a machine. The encounter transfers orbital angular momentum into internal spin and random motion, heating the disks. When ordered motion becomes random motion, thin structures puff up, and the galaxy begins to lose the graceful precision of a spiral. The stellar velocity dispersion rises, and the disk becomes dynamically hotter, meaning stars wander more widely above and below the plane. The redistribution is the real violence, because it changes what orbits are allowed and which ones become unstable. Stars that once traced thin circular paths are kicked into thicker, more eccentric trajectories. Some are thrown outward into the halo, while others are nudged inward, where the gravitational potential is deeper and the environment is harsher. Even without collisions, the map of safe, quiet orbits shrinks, and the galaxy becomes a place of continual adjustment. Bring back Chapter 3's streams as a preview of scale, because we have already seen how debris remembers an encounter. The giant stellar stream is a small rehearsal, while the first pass generates tails that can span hundreds of thousands of light years. In wide field views, those tails can look like pale brushstrokes, evidence that galaxies are not rigid objects but responsive fluids of stars. Their faintness is itself a clue, because it means the material is spread thin, stretched by tidal shear across enormous distances. Mention warps and lopsidedness as expected outcomes, not special cases reserved for dramatic simulations. Outer disks bend like sheets under uneven load, and the warp can persist long after pericenter. Gas, being dissipative, can settle into new planes, while stars keep their stirred-up inclinations for far longer. The result is a galaxy that looks slightly wrong from many angles, like a record that has been gently warped but still plays. The halos also respond, even though they do not shine and cannot be photographed directly. Dark matter particles interpenetrate, but the combined potential changes and wakes form that deepen the breaking. In effect, each galaxy plows through the other's halo, raising a gravitational swell behind it that steals speed. The breaking is slow, but it is relentless, and it is strongest where the halos are densest. Name the bridge explicitly, because it is a key beat the eye can follow across the sky. A luminous and gaseous connection can form between the galaxies, a temporary corridor shaped by tides. In ultraviolet it would glow with young stars, in radio it would whisper with hydrogen, stretched into a filament by gravity. In optical light, it may look like a faint milky thread, too delicate for casual eyes, but unmistakable in long exposures. Now shift to gas, because gas does collide even when stars do not, and that difference changes everything. When the gaseous disks overlap, clouds compress, shocks propagate, and energy is radiated away as heat and light. Unlike stars, gas can lose energy efficiently, so it can sink, pile up, and ignite new activity. Where stellar orbits can only be bent, gas can be crushed, cooled, and redirected into dense lanes. State the starburst trigger clearly because the mechanism is physical, not mystical. Compression raises density above thresholds for gravitational collapse, and shock fronts can sweep through spiral arms like moving pressure walls. Where the gas cools and fragments, it forms giant molecular clouds, cold, dense nurseries that can spawn clusters by the thousands. The chemistry matters too, because metals and dust help gas radiate heat away, making collapse easier once the squeeze begins. The result is elevated star formation in bursts, especially in the inner regions where inflows concentrate fuel. Torques remove angular momentum from gas and funnel it inward, feeding central star-forming rings. Those torques arise because the gravitational potential becomes asymmetric, and gas responds by spiraling toward the deepest part of the well. In images, the inflow can resemble dark, braided dust lanes feeding a bright center, like rivers converging into a glowing basin. Supernova rates rise because massive stars live fast and die young, often within a few million years. A starburst front-loads the deaths, and the galaxy briefly becomes richer in cosmic rays and hard radiation. The interstellar medium becomes a storm of expanding shells, hot bubbles, and turbulent mixing layers. Over time, these explosions can carve superbubbles that vent into the halo, carrying hot gas and magnetic fields outward. Tie this to habitability without overpromising doom, because the story is subtle and uneven across space. Most planetary systems survive the stellar flybys, but their radiation environment can change as nearby supernova probability increases. The danger is statistical rather than certain, an elevated risk that depends on where a system sits relative to star-forming regions. A quiet orbit far from the central frenzy may remain stable, while a region near clustered massive stars becomes a harsher neighborhood. Habitability zones are not only about distance from a star, because biology also lives inside a galactic ecosystem. They are also about the galactic neighborhood, because sterilizing events depend on local star formation density. A quiet outer disk can be comparatively gentle, while a crowded starburst core can be chemically rich, but radiatively unforgiving. The paradox is that the same processes that enrich planets with heavy elements can also increase the frequency of dangerous radiation events. In a starburst, the risky zones expand around clusters and spiral arm complexes, where massive stars are born in tight groups. The average interstellar medium becomes more turbulent, and magnetic fields can be amplified. That amplification happens as gas is sheared and compressed, winding field lines tighter and driving stronger synchrotron emission. Radio telescopes would see the system brighten in broad halos of non-thermal glow, tracing particles accelerated by shocks. Gas inflows can also feed central black holes, though the outcome is model-dependent and sensitive to how gas fragments. Even modest accretion episodes can light up nuclei and add another radiation source. In some futures, the cores could flare as active galactic nuclei, while in others they remain comparatively quiet, smouldering rather than blazing. Either way, the central regions become more energetic, and the surrounding gas is forced to respond. Keep the counterintuitive truth in the foreground, because it anchors the viewer against the wrong intuition. The galaxies collide, the gas collides, but the stars mostly miss each other. The spectacle is not a pileup of suns, but a reorganization of trajectories, an invisible rewrite that becomes visible through structure. What looks like fireworks is often the after effect of gravity guiding matter into new densities and new patterns. Now move to the sky from Earth, because the documentary's intimacy depends on perspective and lived experience. The first pass is not only a dynamical event, it is a transformation of the night. The heavens become a calendar, and the calendar becomes a slow-motion warning. Each millennium adds a subtle change, and the accumulated difference becomes a kind of cosmic handwriting across the dark. Start with the present baseline, where Andromeda is a faint smear for dark-adapted eyes on a moonless night. Over millions of years, it brightens, grows, and spreads beyond its familiar oval. Its core becomes easier to pick out, and its extended disk stops being a rumour and becomes a clear, elongated presence. The change would be imperceptible in a lifetime, yet obvious across deep time, like watching a glacier advance one grain at a time. As distance decreases, apparent size increases, and surface brightness changes with structure rather than with simple scaling. Andromeda's disk becomes a wide, textured band, and its dust lanes become obvious features. Those lanes are not empty gaps, but cold, light-blocking clouds that silhouette themselves against the glow of billions of stars. In the best skies, the lanes would look like dark ink strokes, and the bright knots of star-forming regions would sparkle around them. By the time of first pericenta, Andromeda can dominate the sky as an arc that feels almost architectural. It can rival the Milky Way's own band, turning the night into a double galaxy panorama. Two luminous rivers cross the darkness, and the eye struggles to decide which one is home. The scene would be bright enough to cast faint shadows in truly dark places, not from a point source, but from a vast, diffuse glow. Constellations are not destroyed physically, but they are erased culturally and visually, because the background changes. The old patterns are drowned by a new luminous geometry that no ancient skywatcher knew. What happens to navigation, myth, and memory when the sky's familiar anchors are washed out by a brighter, closer spiral? Even the idea of a fixed sky becomes a historical artifact, a belief that belonged to a quieter epoch. The Milky Way itself changes in response, and the change is visible if you know where to look. Our own disk warps, its star clouds shift, and new streams appear as tidal debris crosses the sky. The band of the Milky Way thickens in places, thins in others, and faint arcs appear where stars have been lifted into long, looping orbits. Against that shifting background, the old constellations become like sketches on moving water, recognizable for a while, then gone. Describe the overlap moment as a slow-motion crossing, not a crash, because the timescale is the story. The disks interpenetrate over tens of millions of years, and the sky evolves across many generations. A child might grow old under a sky that is only slightly different, yet the cumulative change across epochs becomes unmistakable. The motion is so gradual that it feels natural, and that is part of its unsettling power. The bridge can appear as a faint band connecting the two spirals, a delicate thread that seems impossible until you remember its scale. The tidal tails can extend like pale ribbons, marking where stars have been lifted into new orbits. In long exposures, the tails would look like ghostly brushstrokes, barely there, yet spanning a third of the sky. If you could speed up time, those ribbons would unfurl and twist, like smoke drawn out by a slow, steady wind. Emphasize that the view depends on where the sun is at that time, because our vantage point is not fixed. Our position in the Milky Way sets the angle, and different simulations place the solar system on different trajectories. Even small differences in the sun's orbital phase can decide whether Andromeda rises as a looming wall or stretches as a diagonal band. The same encounter can look like a near collision in one sky and a majestic flyby in another. Some runs keep the sun in the outer disk, while others loft it into the halo far above the dusty plain. The uncertainty is not drama for its own sake. It is sensitivity to initial conditions. In chaotic multi-body systems, tiny measurement errors become divergent futures, and the galaxy is a vast multi-body system. The irony is sharp. Our forecasts depend on measuring motions so small that they almost disappear into instrumental noise. Bring back M33 as a complicating shadow, because it can change the first-pass environment without stealing the story. If Triangulum has merged with Andromeda earlier, the gas supply and disk stability differ. A prior merger can thicken Andromeda's disk, stir its halo, and seed it with additional streams that later interactions will stretch further. That earlier disturbance can also change how Andromeda's gas responds, making the starburst either sharper or more spread out. If M33 remains separate, it can be torqued, stripped, or slingshotted during the interaction, depending on timing. Its fate changes the debris field and the later star formation history of the remnant. A small companion can still matter, because it adds another source of tidal forcing and another reservoir of gas. In the sky, it could become a third player, faint, displaced, and trailing its own wisps of torn stars. Now connect first pericenter to angular momentum in a single backbone sentence, because this is the engine beneath the visuals. The encounter converts ordered rotation and orbital motion into heat, tails, and inflows, and that conversion decides how quickly the pair can fall back. In simple terms, it is a trade. Graceful motion is exchanged for disorder, and disorder is hard to reverse. Once the disks are heated and the halos are stirred, the system has fewer pathways back to the clean symmetry it once had. Explain why the galaxies do not simply pass and separate forever, because the viewer may expect a flyby in empty space. Dynamical friction in massive halos removes energy, and the tidal tails carry away angular momentum like thrown ballast. Some debris becomes loosely bound and drifts outward, while some remains attached, forming a shared, ragged envelope around both galaxies. The envelope is a kind of common atmosphere, a faint domain where the distinction between Milky Way and Andromeda begins to blur. After pericenter, the galaxies move apart again, but not to their original separation, and not with their original symmetry. The first pass leaves them bound more tightly, with distorted disks and a shared envelope of debris. Their outer regions are now braided together by gravity, and the path back inward has already been shortened. In the wake of the pass, the galaxies look like spirals that have been pulled slightly out of tune, still recognizable, but no longer pristine. Name the timescale for the rebound in broad terms, because it sets anticipation and prevents the event from feeling instantaneous. The interval between first pass and the next close approach is typically hundreds of millions to over 1 billion years. That pause is long enough for new stars to form, for clusters to disperse, and for tidal features to fade at the edges while remaining clear in deep surveys. It is also long enough for observers, if any exist, to mistake the lull for stability, even though the next encounter is already guaranteed by the altered orbit. During that interval, star formation can remain elevated in pockets, then fade as gas is consumed, heated or blown outward. Feedback from supernovae can drive winds that reshape the remaining fuel. Those winds can enrich the circumgalactic medium with heavy elements, spreading the products of stellar evolution into the space between galaxies. Over time, that enrichment changes the raw material for future stars, making later generations more metal-rich and more efficient at cooling. The halos continue to mix, and the barycenter becomes a more obvious dynamical center, even if no bright object marks it yet. Satellites can be captured, exchanged, or stripped as the combined potential deepens. Dwarf galaxies that once orbited peacefully can find their paths altered, their stars peeled away into new streams that wrap the forming system. In a wide simulation view, the scene resembles a slow storm, with small bodies caught in shifting currents around two massive centers. This is where earlier uncertainties reappear as narrative tension, because the details control the pattern of scars. Halo mass, traxiality, and substructure affect tail shapes, stream precession, and the rate of orbital decay. Even the distribution of dark matter clumps can perturb tidal debris, creating gaps and kinks that future astronomers might read like fingerprints. The debris becomes a record of invisible structure, a way to see the unseen by watching what it disturbs. The same physics that shaped Andromeda's past streams now shapes our shared future streams, and the symmetry is unsettling. Galactic archaeology becomes galactic prophecy, using debris as both evidence and forecast. When we map a stream today, we're not only reconstructing a past encounter, we're practicing for the one that will include us. The sky's faint scars are a laboratory notebook written in starlight, and we are learning to read it, reassert the chapter's emotional paradox in one dense beat, because the tone must remain mysterious and precise. The event is beautiful because it is structured, and terrifying because it is indifferent, unfolding on timescales that ignore us. If intelligence survives that long, what stories will it tell about a sky that refuses to stay still? Will it see the encounter as disaster, as renewal, or as a natural phase in the life cycle of galaxies? Return to the counterintuitive line one more time, because it prevents the wrong mental picture from taking root. Stars rarely collide, but galaxies absolutely do, because gravity collides through everything. The collision is change in the rules of motion, and the visible fireworks are only the afterimage of that change. What we call impact is really a shift in probability, a new distribution of orbits that reshapes where matter can gather. Now transition, because the first encounter is not the end of the story, and the rebound is only a breath between impacts. The first pass is only the beginning, and the galaxies will fall back together for the final merge. The next chapter follows what happens after the rebound, when repeated passages erase the original disks. The slow-motion cataclysm continues until two spirals become one remnant. After the first encounter, the galaxies separate, but the separation is a trick of momentum. On the screen, two luminous disks drift apart like ships in fog, yet their invisible mass remains braided together. Their halos stay interlaced, because dark matter extends far beyond the starlight we usually call a galaxy. The orbit is already smaller than before, and the next return is no longer a question of if. Each return pass is shaped by dynamical friction, the gravitational braking that never needs contact. It is counterintuitive in plain language. Nothing touches, yet something slows, because gravity is not only a pull, it is a sculptor of motion. A moving galaxy raises a wake in the other's dark matter, and the wake tugs backward. In a simulation view, that wake looks like a faint, overdense smear trailing behind the intruder, a gravitational footprint written into a collisionless sea. Energy and angular momentum leak into the halo's random motions, and the orbit decays. The halo particles are not arranged like gears, so the energy does not come back in an orderly way. Instead, the system heats, and the tidy orbital energy becomes a broader distribution of speeds. The process is slow because the system is huge, and because most mass is collisionless. The stars and dark matter mostly pass through each other, exchanging momentum through the collective field rather than direct impacts. The merger is drawn out over roughly 4 to 6 or more billion years after first pericenter. That span is long enough for continents to rearrange and for species to rise and vanish, which is a useful reminder of scale. The range comes from uncertain halo masses, shapes, and the still hard transverse motion. Even now, the sideways component of Andromeda's approach is the crucial unknown, because it sets how deeply the first plunge cuts. A glancing geometry stretches the schedule, because the first pass steals less orbital energy. The tidal disturbance is still dramatic, but the galaxies keep more of their initial momentum, and the next loop is wider. A more direct passage tightens the spiral, because the wakes form deeper in denser halo regions. Dense regions amplify dynamical friction, since the gravitational wake grows stronger where more mass can be rearranged. Between passages, tidal debris keeps moving, and some of it falls back. In wide-field imagery, the tails arc like pale ribbons, their surface brightness low but their reach immense. The tails are not only scars, they are levers that carry angular momentum outward. They act like long handles on a spinning system, letting the inner regions shed rotational support while the outskirts absorb it. The second approach arrives with less symmetry, because the first pass already heated both disks. Spiral arms that once traced density waves become less coherent, and the thin stellar layers puff upward. Ordered rotation is weakened, and more stars now move on eccentric, tilted paths. A face-on view would show the spirals losing their crisp geometry, as if the pattern is being erased by repeated shaking. This is the point where spirals begin to forget they were spirals. A thin disk depends on cold, coherent orbits, and repeated tides turn coherence into dispersion. Cold here is not temperature in the everyday sense, but low random velocity compared with rotation. When random motions rise, the disk thickens, and its ability to hold a delicate spiral pattern fades. Violent relaxation begins in earnest as the potentials overlap and change quickly. The gravitational field is no longer a stable bowl, but a shifting landscape whose contours move on timescales comparable to stellar orbits. Stars respond to a time-varying gravitational field, and their energies are redistributed toward a new equilibrium. In visual terms, the bright knots of the disk smear into a broader glow, while the center grows denser and more dominant. Violent relaxation is not a collision of stars, it is a reshuffling of orbits by a fluctuating potential. Individual stars remain separated by light years, so direct hits are extraordinarily rare even in the chaos. What changes is the bookkeeping of energy and momentum, as the collective field trades order for a smoother statistical balance. The result is a smoother light profile and a rounder, thicker body, with less memory of the original disk planes. The end state is likely an elliptical or a lenticular galaxy, and the difference depends on how much gas remains. This distinction has a history in astronomy, because early observers classified galaxies by appearance long before the physics was clear. Ellipticals look like smooth, featureless ovals, while lenticulars sit between spirals and ellipticals, keeping a disk but losing the arms. If gas is depleted or expelled, the remnant becomes redder and more spheroidal, because new blue stars stop forming. If enough gas survives to settle, it can rebuild a disk and produce a lenticular form. Gas can radiate energy away through atomic and molecular lines, so it can cool and flatten again after being stirred. Residual angular momentum and late gas accretion decide whether any thin structure returns. The disk that reforms would not be the old Milky Way disk revived, but a new arrangement assembled from leftovers. The local group's third body still matters, even this late in the story. M33 is smaller, but its orbit and gas content let it act like a perturbing weight on a larger machine. It can donate gas, torque the encounter plane, or be stripped into the growing common envelope. In some outcomes it is swallowed early, and in others it survives longer as a battered companion trailing its own faint streams. Earlier streams in Andromeda's halo become a quiet foreshadowing here, because the same physics scales up. The progenitor that made the giant stellar stream was a rehearsal for Milkomeda's larger mixing. Those earlier events taught astronomers that halos are not smooth, but layered with debris from past meals. Now the meal is immense, and the debris field becomes a signature written across hundreds of thousands of light years. As the cores pass again and again, gas behaves differently than stars. Gas clouds collide, shock, radiate energy, and sink toward the deepest parts of the combined potential. Where stars behave like test particles, gas behaves like a fluid, and fluids can lose energy quickly. In a high-resolution render, you would see filaments compress, brighten, and funnel inward, tracing the gravitational drain. Those inflows trigger starbursts that are intense but finite, because fuel is limited. A burst converts cold gas into massive stars, and massive stars quickly return energy. Their ultraviolet light ionizes surrounding clouds, and their winds carve cavities before the first supernova even arrive. The burst is a brief flare in cosmic time, but it can dominate the galaxy's luminosity while it lasts. Supernova feedback injects heat, turbulence, and momentum into the interstellar medium. Expanding shock fronts overlap, turning calm molecular clouds into a churning, multi-phase mixture of hot plasma and dense clumps. It can both compress nearby clouds to form more stars and disrupt clouds to halt collapse. That dual role is part of the mystery of regulation, because the same explosion can create and destroy star formation depending on local conditions. At the same time, central inflows can feed the supermassive black holes. Even if the nuclei were quiet before, the merger can supply dense gas that changes the accretion state. Gas loses angular momentum through torques, shocks, and gravitational instabilities, and that loss is what allows it to fall inward. The central parsecs become crowded with fuel, dust, and intense radiation fields, a place where ordinary galactic calm cannot survive. If accretion rises, an active nucleus can appear, and its winds can dominate the gas budget. The bright core would outshine much of the galaxy in some wavelengths, turning the center into a beacon. AGN feedback can drive outflows that remove star-forming fuel and heat the circumgalactic medium. In visual terms, bipolar cones of energized gas can punch outward, their edges glowing where they slam into cooler material. The fate of the gas becomes a competition between consumption and expulsion. Some gas is locked into stars during bursts, and some is blown outward into a hot, enriched halo. The outflowing material carries metals forged in stars, so the halo becomes chemically upgraded, not just inflated. What remains behind is determined by timing, because winds that arrive early can starve later star formation. The balance depends on initial gas fractions, merger geometry, and how efficiently feedback couples to dense clouds. Coupling is the key phrase, because energy that escapes through low-density channels does less work. A gas-rich encounter builds a brighter central starburst, but it also powers stronger winds. A gas-poor encounter is quieter, yet it more easily ends in a quenched red remnant. As gas is driven inward, metallicity rises in the center, and dust becomes more abundant. Metals enable efficient cooling, and dust grains provide surfaces where molecules can form, which helps clouds collapse. That dust both cools gas to enable collapse and obscures the regions where collapse is happening. In infrared vision, the hidden centers would glow warmly, revealing star formation that optical light cannot easily show. Over time, the system's star formation rate declines as the easy fuel is used up. The remaining gas is hotter, more diffuse, or pushed to larger radii where it is harder to compress. The remnant transitions from a blue, structured pair into a redder, smoother single galaxy. Its colour shift is not cosmetic but demographic, marking the change from short-lived massive stars to longer-lived lower-mass populations. Even as the visible disks dissolve, the dark matter halos continue to mix with little resistance. Their particles pass through, but their combined potential becomes one, and the barycenter stabilizes. In a gravitational map, the two wells merge into a single deeper basin, and the outer halo becomes a blended archive of both histories. The halo's shape may remain somewhat triaxial for a time, which matters because non-spherical potentials keep stirring stellar orbits. The central black holes follow a different clock, set by gravity on smaller scales. Sagittarius A star and M31 star sink toward the new center through dynamical friction against stars and dark matter. The black holes are tiny compared with the galaxies, yet they are heavy enough to feel the drag of the surrounding swarm. Their spiral is like a slow descent through a crowded ballroom, where each gravitational encounter steals a little momentum. First, they form a bound binary, because the merger brings their nuclei into the same deep potential well. At that stage, the two black holes orbit each other inside a shared stellar cusp, and the surrounding stars become participants. The binary hardens by scattering nearby stars, ejecting them and carving a lower density core. Those ejected stars can be flung onto wider orbits, and a small fraction may even become hypervelocity runaways. This is the final parsec problem in a new setting, and the solution depends on supply. The phrase comes from decades of theoretical work, because a binary can stall if it runs out of stars to fling away. Gas torques, triaxial stellar distributions, and repeated perturbations can keep feeding the binary with stars. In other words, the galaxy's imperfect shape and leftover gas can keep the loss cone refilled, preventing the inspiral from freezing. As the separation shrinks, gravitational waves take over and the inspiral accelerates. The system radiates energy and space-time ripples, invisible to eyes but measurable in principle. The waveform would sweep upward in frequency and amplitude, a rising chirp that carries the signature of mass and spin. It is a reminder that gravity is not instantaneous action, but a field with its own dynamics and its own radiation. The final plunge ends in a single black hole, and the remnant rings like a struck bell. The ring down is the settling of the warped horizon into a stable Kerr shape. In a visualization, the distorted horizon smooths out as if a vibrating surface is damping, leaving a clean, rotating geometry. The energy lost is not a small detail, because it is mass energy leaving the system at light speed. Gravitational waves carry away mass energy and angular momentum, and the merged whole can receive a recoil kick. The kick depends on mass ratio and spin alignment, and it can displace the nucleus. If the spins are misaligned, the asymmetric wave emission acts like a rocket exhaust, pushing the remnant. The displacement might be temporary, but even a brief offset can disturb central stars and gas, leaving subtle structural fingerprints. By then, Milkomeda's stellar body is mostly pressure-supported rather than rotation-supported. Random motions dominate, and the light profile resembles the smooth envelopes seen in elliptical galaxies. The stars behave more like molecules in a warm gas than like cars on a circular track, though gravity still binds them tightly. In the outer regions, faint shells can appear where tidal debris piles up at orbital turning points, like surf lines on a dark beach. Yet not all order is erased, and that is why lenticular outcomes remain plausible. Some stars can retain partial rotation, especially if the encounter geometry preserves a net angular momentum axis. If gas settles into a new plane after the chaos, it can rebuild a faint disk around a bulge. That disk may be thicker and more subdued than the Milky Way's current one, but it would still be a recognizable plane of structure. The remnant's appearance depends on what survives the feedback era. Strong winds and heating favor a quenched elliptical, while retained gas and angular momentum favor a diskia lenticular. The difference is visible in the distribution of young stars, dust lanes, and residual spiral-like features, if any can re-emerge. In either case, the old identity of two separate galaxies is gone, replaced by a single gravitational organism. The new galaxy is born through destruction, and the creation is statistical rather than designed. Gravity does not plan a shape. It explores possibilities and leaves the stable ones behind. This is the deeper lesson of hierarchical assembly. the principle that large galaxies are built by repeated mergers and accretions. When we watch Milkomeda form, we are watching the same process that built many ellipticals long before Earth existed. Now narrow to the question of individual stars, because the viewer needs a personal scale. In mergers, stars rarely collide, but their orbits can be radically reassigned. The emptiness between stars is so vast that even in dense regions, direct impacts are practically non-existent. What changes is the gravitational map they navigate, and a small change in the map can redirect a star over billions of years. The Sun's trajectory is not fixed to the present disk, because the disk itself is dissolving. Tidal torques and potential fluctuations can lift stars into the halo or push them outward. The Sun may find itself on a more eccentric orbit, rising above and below any surviving plane. In a sky view from that future, the familiar Milky Way band would be replaced by a broader, less structured glow. Some simulations place the solar system farther from the centre after coalescence, and some place it closer. The spread reflects chaotic sensitivity and uncertain initial conditions, not narrative certainty. Tiny differences in the first passage can cascade into different outcomes after multiple returns. That sensitivity is not a flaw, but a property of nonlinear gravitational systems with many interacting components. Frame it as probability, not prophecy, because the system is too complex for a single track. The Sun is more likely to avoid the dense central core than to be driven into it. The core is small compared with the total volume, and most stellar orbits do not thread it. Still, more likely is not guaranteed, and the uncertainty is part of the honest tension of the story. Even an outward-flung orbit is not safety in the everyday sense. It is a different environment. The night sky would change, the background radiation field would shift, and nearby stellar densities would differ. In the outskirts, the sky can be darker in visible starlight, yet richer in faint halo structure. In the inner regions, the sky can be crowded with stars, and the rate of close supernovae becomes a more serious statistical concern. The main hazards are indirect and uneven, tied to where starbursts concentrate. A system far from star-forming cores sees fewer nearby supernovae, while inner regions face higher rates. The danger is not a single apocalypse, but an elevated probability of harmful events over long intervals. It is a reminder that habitability is not only about planets, but also about galactic neighbourhoods. During peak activity, cosmic rays, UV, and X-ray backgrounds rise, especially near the nuclei. Those backgrounds can alter atmospheric chemistry and increase radiation doses at planetary surfaces depending on shielding. If an AGN phase occurs, its influence is directional and time-limited, but potentially intense. Jets and winds do not illuminate the galaxy evenly, so a planet's risk depends on where it sits relative to the beam. Life, if it exists then, would not face a universal sterilization event. It would face a changing risk landscape, shaped by distance from clustered star formation and by shielding in atmospheres and magnetospheres. Some worlds might endure with little notice, while others are pushed into repeated stress. The merger is dramatic in the sky, but biology experiences it as a long sequence of altered probabilities. The merger also changes astronomy itself, because the sky's reference frame is rewritten. Constellations dissolve, the Milky Way band loses its familiar geometry, and Andromeda's identity disappears into one glow. For a time, the most striking feature would be the companion's stretched light, a bright smear across the sky that slowly reshapes night after night. Then even that distinction fades, as the two become one luminous structure. For a time, observers inside Milkomeda would see tidal shells and streams as bright features. Those structures would be the new fossil record, replacing the old streams we used to read Andromeda's past. Shells can appear as nested arcs around the remnant, and streams can wrap like ghostly bracelets, each one a record of an earlier passage. The galaxy would wear its history on the outside, visible to anyone patient enough to map faint light. The same question returns in a sharper form, because the merger is a test of what galaxies are. Is Andromeda a place, a pattern, or a phase in a longer cycle of assembly? The answer is uncomfortable, because it suggests that identity in the universe is often temporary. A galaxy can be both a home for stars and a transient configuration of matter, destined to be remade. Even if stars do not collide, environments change, and environments matter for biology. The fireworks are mostly gas and radiation, but the long-term outcome is a quieter, older stellar population. After the bursts and winds, the remnant settles into a slower rhythm, dominated by aging stars and fewer new births. The sky becomes calmer, though the memory of the violence remains in the galaxy's shape. Ask the uncomfortable extension without answering it yet, because the mystery must remain. If life can persist through the merger, could it also exist in Andromeda now under a different chemical history? And if it does, what would it see when our galaxy begins to swell in its sky, growing from a faint patch to a dominating presence? The question is not only scientific but philosophical, because it forces us to imagine observers on both sides of the collision. And if intelligence survives long enough, it inherits a new sky and a new cosmic isolation. As the universe expands, distant galaxies fade beyond reach, and Milkomeda becomes the main island left. The cosmic web thins in the viewable distance, not because it disappears, but because light can no longer catch up. Future astronomers may have to infer the broader universe from fossils of radiation and from the physics written into local matter. Transition. The coalescence ends the dance, but it begins a different era of observation. The next chapter follows the aftermath, when the new galaxy settles and the wider universe grows lonelier. The camera pulls back from the bright centre to the faint outskirts, where streams still drift like smoke. The violence is over, but the consequences continue to unfold in slow motion. Andromeda was never only a destination, it was a time-delayed message about change. In Milkomeda, that message becomes local, and the cost of creation becomes visible in our own night. The same laws that shaped distant galaxies now reshape the one that once felt permanent. The final image is not an ending, but a new equilibrium, quiet, massive, and haunted by the paths that led there. Andromeda is still a smear of ancient light, but the question narrows toward intimacy as we watch it drift closer. What is Andromeda truly like as a habitat, not a target, as our galaxies move toward merger? On screen, the galaxy looks serene, a soft oval with dark lanes stitched through its glow, yet every bright patch is a crowd of suns, and every shadowed ribbon is dust where stars are still being born. When we say Andromeda, we're naming a whole ecology of orbits, elements, and radiation. We know exoplanets in the Milky Way by the thousands, because nearby stars can be monitored repeatedly with exquisite precision. A star close to Earth is not just a point of light, it is a measurable object whose flickers can be tracked night after night. That repeated access is the quiet superpower behind most planet catalogues. In Andromeda, individual stars are mostly unresolved at planet-hunting precision, and the galaxy is too far for routine radial velocity work. Radial velocity depends on detecting a star's tiny wobble, often measured in meters per second, through subtle shifts in spectral lines. At 2.5 million light-years, Andromeda's stars are faint, blended, and stubbornly unwilling to yield that kind of detail. A transit survey needs stable photometry on single stars, and Andromeda's crowding turns many suns into blended pixels. The camera does not see one star dim, it sees a whole neighbourhood dim, or appear to dim, because multiple sources share the same detector footprint. Even with space telescopes, a planet's tiny dip is diluted by neighbours, and false positives multiply. Those false positives have familiar faces, even in our own galaxy, and distance makes them worse. Eclipsing binary stars can masquerade as transiting planets when their light mixes with a brighter star nearby. Variable stars can mimic a periodic dip, and instrumental systematics can imprint patterns that look planetary until they are tested. Direct imaging is even harder, because the planet is dim, and the star is bright, and the separation is microscopic. At 2.5 million light-years, the angular separation of an Earth-like orbit is effectively zero, and the contrast problem becomes brutal. Even a perfect coronagraph cannot easily carve a planet out of a glare that never truly spreads apart. There is also a physics limit hiding under the engineering. Diffraction sets a fundamental scale for how finely a telescope can separate two close points of light, and Andromeda pushes that scale to extremes. To resolve an Earth, sun separation at that distance would demand an aperture so vast it becomes more like an array the size of a solar system. So we infer Andromeda's planets by proxy, using physics that scales beyond our neighbourhood. We ask what kinds of stars exist there, what elements they contain, and what hazards dominate their skies. The method is indirect, but it is not guesswork. It is population science, built from what galaxies reveal when you cannot visit. Microlensing is the one method that can reach across a galaxy because it does not require resolving a planet directly. A foreground star briefly magnifies a background star, and a planet adds a short telltale perturbation. The effect comes from general relativity, where mass bends space-time and light follows the curve. Visually, it is like watching a distant candle flare as an invisible lens slides between it and the camera. The brightening is smooth, predictable and temporary, and then the planet's presence adds a sharp wrinkle. That wrinkle can last hours or days, and it is the closest thing we have to a planet's fingerprint at extra-galactic range. In practice, microlensing in Andromeda is hard because both lens and source often sit inside the same crowded field. The events are rare, the light curves are noisy, and the cadence must be relentless. Observers need to stare for long stretches, because the moment you look away is the moment the anomaly can happen. The historical context matters, because microlensing was once a gamble even in the Milky Way. Early surveys in the 1990s used it to search for dark matter in the form of compact objects, and they learned how unforgiving the statistics can be. That experience became the toolkit we now adapt for Andromeda, where every photon is expensive. Even when the sample is small, statistical constraints exist and they matter. The rate of microlensing anomalies can bound the abundance of Jupiter mass companions, and it can hint at the prevalence of wide-orbit planets. Wide orbits are crucial because microlensing is naturally sensitive to planets farther from their stars than transits usually find. There is a subtlety here that the narrator should not hide. Microlensing events do not repeat, and they rarely reveal the host star's full identity with certainty. What we gain is a probabilistic census, how common certain planet masses and separations might be, rather than a list of worlds we can revisit. These are not planet catalogues with names and atmospheres, and the documentary should admit that clearly. They are probability statements about populations, and they are our first foothold beyond the Milky Way. And even that foothold is enough to change the scale of the question. Now the story turns from detection to ingredients, because planets are chemistry made stable. Rocky worlds require heavy elements, and heavy elements are forged in earlier generations of stars. Every atom of silicon in a mountain and every atom of iron in a core began as stellar ash. Metallicity is astronomy's shorthand for everything heavier than helium, and it correlates with planet formation efficiency. More metals mean more solid grains, faster core growth, and more opportunities to build terrestrial planets. In plain language, a metal-rich disk has more construction material before the gas fades away. In protoplanetary disks, those grains collide, stick, and grow into pebbles, and then into kilometre-scale planetesimals. Once planetesimals exist, gravity takes over, and growth can accelerate into embryos and full planets. Metallicity does not guarantee success, but it shifts the odds in favour of building something durable. The correlation is strongest for giant planets, which need massive cores before gas disperses. If the core forms late, the disk's hydrogen and helium are already gone, and the chance to become a gas giant vanishes. For small rocky planets, the dependence is weaker, but metals still set the budget for dust and rock. Andromeda's metallicity is not uniform because galaxies are not well stirred. Its bulge is generally more metal-rich, shaped by early rapid star formation and repeated enrichment. When star formation is intense, supernovae quickly seed the gas with heavy elements, and the next stars inherit that richness. Its disk shows a gradient, with higher metallicity toward the centre and lower metallicity outward. That gradient is measured through stellar spectroscopy, H2 region emission lines, and the colours of old populations. Each method is a different kind of thermometer, translating light into chemical history. Spectroscopy, in particular, is a slow conversation with photons. Absorption lines reveal which elements are present and how abundant they are relative to hydrogen. In Andromeda, we often rely on the brightest traces, giant stars, clusters, and glowing nebulae, because faint sun-like stars are too dim to interrogate individually. The gradient implies a trade-off that feels almost designed to confuse us. Inner regions have more building material for planets, but they also host denser stellar environments and stronger radiation fields. Outer regions are calmer and less crowded, but their lower metallicity can slow the formation of rocky worlds. The galactic map of habitability is therefore a balance, not a single sweet spot. It is a landscape of probabilities, where chemistry rises one way and danger rises another. If the camera could fly through Andromeda, the best neighbourhoods would not glow with certainty, they would shimmer with likelihood. Andromeda's large bulge matters here, because bulges are old and crowded. Old can mean stable in time, because the most violent star-forming era has passed, but crowded can mean frequent close passes. In a dense field, gravity is never truly quiet, and the sky has more chances to surprise you. Disk versus bulge is not just morphology, it is a difference in planetary neighbourhoods. A star in the thin disk may keep a quieter orbit, while a bulge star may live in a higher density sea. The same planet, placed in those two environments, could face radically different long-term odds. This is where earlier chapters echo in a new register, because mergers shape chemistry and risk together. Andromeda's past accretions built streams and shells, and they also mixed metals and stirred star formation histories. The galaxy's halo is not smooth, it is a museum of disrupted companions. A stream is a fossil of gravity, but it is also a fossil of enrichment. Accreted dwarfs can be metal poor, and their debris can seed the halo with stars that formed with fewer heavy elements. When we see a faint arc around Andromeda, we are also seeing a chemical signature stretched across space. So Andromeda's halo may host many stars with low metallicity and fewer rocky planets. That does not forbid life, but it shifts the odds and the timescales for complex chemistry. It invites a question that sounds philosophical but is actually physical. How much metal is enough to build a stable, wet world? Now we add the next layer, because habitability is not only about making planets. It is also about surviving the radiation ecology of a galaxy. A planet can form perfectly and still be stripped, sterilized, or battered into geological chaos. Supernovae are the obvious threat, because they deliver intense UV, X-rays, and cosmic rays. A nearby explosion can erode atmospheres, damage ozone layers, and raise mutation rates beyond repair. The danger is not just the flash, but the long tail of energetic particles that can linger. Distance is the key variable, and it is unforgiving. A supernova within a few tens of light years could be catastrophic for Earth-like life, while 100s of light years away might be a mild stressor. In a dense region, the average distance to the next explosion shrinks, and that changes everything. The risk depends on distance and frequency depends on star formation rate and stellar density. Dense regions create more massive stars per volume, and massive stars are the supernova factories. When a galaxy forms many massive stars, it is also manufacturing short-lived time bombs. Andromeda today forms stars more slowly than the Milky Way, which may reduce the present supernova rate. Its gas content is lower, and its spiral arms are less vigorously lit with newborn clusters, but its central regions still host older populations and potential Type Ia supernovae over long times. Type I events are different, and their difference matters for habitability. They arise from white dwarfs in binary systems, and they can occur billions of years after star formation peaks. That means even an old bulge can still produce explosions, spaced out in time but persistent across epochs. Gamma-ray bursts are rarer, but they are more extreme, and their beams can sterilize across kiloparsecs. Long GRBs prefer low metallicity environments, which may push their likelihood outward or into accreted components. A low metallicity massive star can retain more angular momentum, a condition thought to favour some GRB engines. Short GRBs come from compact object mergers, and they can occur in older populations, including bulges and halos. Their rate is uncertain, but their existence forces humility about low-frequency catastrophes. A single event is unlikely, yet over billions of years, unlikely things become part of the statistics. Active galactic nucleus activity is the third hazard, and it ties back to Andromeda's central black hole. M31's nucleus is quiet now, but quiet is a state, not a guarantee, especially across cosmic time. Black holes feed episodically, and their outburst can rewrite the inner environment. An AGN phase can flood the inner galaxy with hard radiation and drive winds that reshape gas. The danger is strongest near the centre, and it fades with distance, but it can still set a hostile inner boundary. Even if the radiation is not continuously lethal, it can alter atmospheres and chemistry in ways that compound over time. Dense stellar environments add another kind of risk that is not radiation at all. Close stellar encounters can perturb Oort cloud analogues, raise comet impacts, and destabilize wide planetary orbits. In a calm disk, comets are a distant reservoir, but in a crowded bulge, they can become a recurring hazard. In the bulge, typical separations are smaller, and the encounter rate rises. A passing star does not need to collide to cause trouble. It only needs to tug at the outskirts of a planetary system. Even if planets exist there, long-term stability may be harder to maintain over billions of years. So the question becomes geographic, because a galaxy has neighborhoods with different rules. Astronomers call this the galactic habitable zone, a ring or band where metals are sufficient and hazards are tolerable. The phrase is useful, but it is also a simplification that can mislead if taken too literally. The concept is not a single line, and it is not universal across galaxies. It is a moving target that changes as star formation shifts, as metallicity builds, and as dynamical heating rearranges orbits. A galaxy evolves, and the best region can migrate outward as enrichment spreads and inner hazards persist. In Andromeda, the inner disk may offer high metallicity with moderate hazard, depending on supernova clustering and AGN history. The outer disk may offer lower hazard with lower metallicity, but still enough for rocky planets. The documentary can linger on that ambiguity, because it is where science becomes honest. The extreme center is likely the least hospitable, because density and radiation both climb. The far halo is likely chemically poor, and it may host fewer terrestrial planets, even if it is quiet. Between those extremes lies a broad, uneven middle where the trade-offs can sometimes align. This is the same balancing act we suspect in the Milky Way, but Andromeda's different history shifts the parameters. Its larger bulge and different merger record may push the optimal zone outward, or make it patchier. Patchiness is not a flaw in the idea, it is the reality of spiral structure and orbital migration. Patchiness matters, because spiral arms are not uniform factories. A star's orbit can cross arms, and each crossing changes its exposure to star-forming regions and nearby supernova probability. Over billions of years, a star does not stay in one postal code, even if it stays in one galaxy. Stable, long-lived planetary systems favour circular, low-perturbation orbits in relatively calm disk regions. They also favour stars that are not too massive, because long-lived suns give lifetime to iterate. A star like the Sun offers billions of years of steady light, and that patience may be essential. So the best candidates are likely mid-disk, metal-enriched and dynamically settled, far from the central crowding. That is a probabilistic claim, but it is the best kind we can make today. It is also a reminder that habitable is a spectrum, not a switch. Now we widen again, because even if Andromeda has habitable worlds, the next question is contact. The Fermi paradox returns, not as a slogan, but as a silence that grows louder with distance. If life is common and intelligence is durable, then a galaxy with 1 trillion stars should not be quiet. Yet the sky, even in our own galaxy, offers no unambiguous engineering signature. We see pulsars, quasars, and supernova remnants, and we learn to recognize nature's extremes. The unsettling part is that nature is loud, and any technology must compete with that astrophysical noise. Andromeda adds scale and discomfort, because it multiplies the number of possible civilizations. If it is also silent, the paradox deepens, unless our assumptions about detectability are wrong. Perhaps advanced societies do not build the kinds of beacons we imagine, or perhaps they do, but rarely and briefly. At extragalactic distances, most ordinary radio leakage is invisible to us. A broadcast that seems loud at home fades with inverse square law, and it drowns in cosmic background and instrument limits. By the time it crosses intergalactic space, it is not a message, it is a whisper lost in static. Only extreme beacons would stand out, like narrowband high-power transmitters aimed deliberately, or planet-scale energy use producing waste heat. Even then, we must know where and when to look. A beacon that sweeps like a lighthouse could miss us for centuries, and we would never know it existed. Optical and infrared techno-signatures are plausible in theory, but they are ambiguous in practice. A bright industrial spectrum can mimic astrophysical lines, and waste heat can hide under dust emission. In Andromeda, dust lanes already glow in infrared, and they can mask the very excess we would hope to see. A civilization could also choose quietness, or it could communicate in ways we do not search for. Silence does not prove absence, but it does constrain the simplest stories. It asks whether intelligence is rare, short-lived, or simply uninterested in broadcasting across a void. Time is another filter that makes the paradox sharper. A signal must be transmitted during the window when we are listening, and the light travel time means we see Andromeda as it was long ago. Every observation is a time machine, and the time machine does not ask our permission. If a civilization rose and fell there 1 million years ago, its radio era could be over, and we would only now receive its last whispers. If it rose 10 million years ago, even those whispers may have already passed Earth before we built antennas. The universe is full of missed appointments, missed by physics, not by choice. The merger theme returns here in an unexpected way, because collisions are also information mixers. Over billions of years, stars migrate, disks heat, and any civilization's local sky and risk profile changes. A long-lived society would need to plan across changing galactic neighborhoods, not just changing climates. Survival would belong to those who learn to think in cosmic time, or those who leave. That thought is not science fiction. It is the logical extension of orbital dynamics and stellar evolution. If a home region becomes riskier, the only permanent solution may be mobility on scales we barely comprehend. Now transition, because the chapter's intimacy must turn into a challenge of reach. If Andromeda might host worlds, could we ever touch them, or even send something that can? The camera pulls back, and the space between galaxies becomes the main character. The distance is not just large, it is a wall built from energy and time. Chemical rockets cannot cross millions of light years in any meaningful human time frame, and even fusion concepts remain speculative. The problem is not navigation, it is momentum. Pushing mass to relativistic speed without turning the ship into a star. A probe at 1/10 of light speed still needs tens of millions of years to arrive. That is longer than civilizations may last, and longer than languages remain stable. It is long enough for continents to drift, for species to rise and vanish, and for the mission's original purpose to become mythology. Even sending information is constrained by the same geometry. We can transmit light, but we cannot force it to arrive sooner than light allows, and we cannot guarantee anyone is listening. Communication across intergalactic space is not a conversation. It is a message in a bottle thrown into a dark ocean. So the realistic near-term bridge is not travel, but light and gravity. We can search for microlensing signatures, map metallicity gradients, and infer hazard fields from supernova remnants and high-energy emission. We can also compare Andromeda's stellar populations to ours, and test whether planet formation seems universal. We can also search for engineered beacons that would be visible across intergalactic space. If any civilization wanted to be found, it would need to build for distance, not for neighbours. That requirement alone is revealing, because it suggests that being detectable may be a deliberate choice, not an accidental byproduct. Andromeda then becomes a mirror for our own future choices. If we ever broadcast, we must decide whether we are whispering locally or shouting across the void. The decision is technical, but it's also ethical, because it defines what kind of presence we want to be. The central question tightens again, because Andromeda is not only coming toward us, it is also sending us a time-delayed message about how galaxies build worlds and how worlds endure. When we study its gradients, its hazards, and its silence, we are also studying our own long-term odds. In the next chapter, the documentary turns from the possibility of life to the mechanics of reaching. The void between galaxies is not empty, but it is still a barrier, and the barrier defines the stakes. And as Andromeda approaches, slowly, inevitably, we are left with a final question. What would we choose to send into that dark? A faint smear of light hangs in the night, and it tempts us to call it reachable, like a lantern across a dark field. Every photon from Andromeda began travelling before our cities, before our stories, before our names, and it arrives already aged by distance. In a telescope, the galaxy looks calm and orderly, but that calm is an illusion created by time delay. The central question sharpens into a dare. What is Andromeda truly like, and what would it mean if we could go? Between the Milky Way and Andromeda lies 2.5 million light-years of near-perfect emptiness, a span so large it resists metaphor. In maps it looks like a simple gap, a clean black interval between two bright islands. In physics it is a sentence measured in energy, time, and error budgets, with every clause written in unforgiving units. The void is the chapter's antagonist, because it does not fight, it only waits, and it wins by letting clocks run. Start with the distance problem, because it breaks intuition immediately and keeps breaking it as you do the arithmetic. At 1% of light speed, the crossing takes about 250 million years. At 1/10 of light speed, it still takes about 25 million years in the galaxy frame, longer than our species has existed. Even at half light speed, it takes roughly 5 million years before you count acceleration and braking. These are not cinematic numbers. They are geological numbers, the kind that belong to continents and ice sheets. These numbers are not pessimism, they are geometry, and geometry is indifferent to ambition. The void is so wide that even heroic speed is swallowed by sheer scale, the way a fast swimmer is still trapped by an ocean. A mission plan becomes a commitment longer than recorded history by orders of magnitude, and the paperwork is written in extinction-level time. The journey's first lesson is that propulsion is not the only barrier. The second lesson is that time behaves differently when speed becomes extreme, and that difference cuts both ways. Relativity enters as soon as we talk about 0.1c to 0.9c, because Newton's comfortable approximations begin to slip. At 0.1c, time dilation is modest, and the crew experiences almost the same duration as the outside universe. At 0.5c, the Lorentz factor is about 1.15, and onboard time shortens, but not enough to rescue a multi-million-year crossing. At 0.9c, the Lorentz factor is about 2.3, and the crew's time is cut by more than half. The ship's clocks and the universe's clocks begin to disagree in a measurable, relentless way. That sounds like a loophole, until you price it in fuel and shielding, and the invoice arrives in exponents. To reach 0.9c, you must pour energy into mass until the ship becomes a relativistic projectile, and even tiny masses become expensive. The kinetic energy per kilogram rises steeply as you approach light speed, and the required propellant ratio becomes punishing for any rocket that carries its own reaction mass. Time dilation can make the trip feel shorter for travelers, but it makes the engineering feel impossible for builders. The universe allows the shortcut, but it charges for it. Acceleration is its own hidden tax, because you do not teleport to cruising speed. A ship that accelerates at 1g for a year reaches about 0.77c, but it also travels a huge distance while accelerating, eating the route before it ever coasts. The midpoint flip and deceleration must match, doubling the required energy and doubling the exposure to hazards. If you reduce acceleration to protect structure and crew, the trip stretches again, and the ship spends longer in the firing range of the void. The void forces trade-offs that never stop, because every solution creates a new constraint. Now compare propulsion candidates, because each one fails differently, and the failure modes are as revealing as the promises. Chemical rockets are eliminated by exhaust velocity and mass ratios, long before intergalactic space even becomes the problem. Electric propulsion is efficient but too low thrust for meaningful fractions of C with large payloads, and time is the one resource you do not have, so the candidates that remain are the ones that treat mass and energy as almost interchangeable. Fusion, antimatter, beamed sails, nuclear pulse, and the slow, brute force answer of generation ships. Fusion is the first serious rung because it is at least anchored in laboratory physics and in decades of hard-won plasma research. Inertial confinement fusion compresses pellets with lasers or particle beams, chasing ignition in microseconds as shockwaves race inward. Magnetic confinement fusion holds hot plasma in fields, chasing stability for seconds and then for hours, while turbulence tries to tear the plasma apart. Both approaches promise high specific impulse compared with chemical engines, but neither has yet delivered a compact, reliable, high-power drive. In a documentary frame, you can almost see the plasma, bright, restless, and unwilling to behave. A fusion rocket must do more than burn fuel, because burning is the easy verb. It must direct exhaust, reject waste heat, and survive neutron bombardment for years without brittle failure, while keeping its magnetic coils and structures aligned. Deuterium-tritium reactions are easier to ignite, but flood the structure with neutrons that damage materials and transmute atoms in place. Deuterium-helium-3 is cleaner but demands rare fuel and higher temperatures, pushing confinement and stability further into the unknown. Even if ignition is solved, the engine becomes a long-duration materials experiment at the edge of what solids can tolerate. Fuel sourcing becomes part of the plot, because a drive is only as real as its supply chain. Helium-3 is scarce on Earth, and harvesting it from gas giants or lunar regolith is a civilization-scale project with mining, transport, and storage across decades. Deuterium is abundant, but the reactor still needs precision manufacturing and constant maintenance, and those needs do not disappear in deep space. A ship that must run for centuries cannot depend on fragile tolerances or rare replacement parts. Fusion is plausible as a concept, yet the void demands a reliability we have never achieved, not even in our most mature machines. Antimatter is the seductive extreme, because its energy density is unmatched, and its math is brutally simple. Matter-antimatter annihilation converts mass directly into radiation and energetic particles, with efficiencies that make chemical fuels look like candles. A gram of antimatter releases energy comparable to large nuclear devices, and kilograms imply world-scale power, the kind that rewrites geopolitics. In equations, it looks like the cleanest path to relativistic flight, a straight line through the rocket equation's worst traps. In engineering, it becomes a containment nightmare, because antimatter is intolerant of touch in the most literal sense. Antimatter cannot touch ordinary matter, so it must be stored in electromagnetic traps, isolated from every surface, every dust mote, every mechanical vibration. Traps require power, stability, and fault tolerance over long durations, and they must survive micrometeoroids and radiation without a single lapse. A single containment failure is not a leak, it is an explosion, and the blast is born inside your own hull. Production is worse because making antimatter is inefficient, expensive, and currently measured in nanograms, a laboratory trick rather than an industrial process. Even if you had antimatter, you must turn annihilation products into thrust, and nature does not make that convenient. Much of the energy emerges as gamma rays that are hard to reflect or collimate, and they pass through matter like ghosts with teeth. You can try to use charged pions with magnetic nozzles, but the system becomes massive and complex with fields that must stay stable under extreme loads. The void does not care that the energy exists. It cares whether you can aim it without destroying yourself, and whether you can keep aiming it for years. Beam propulsion changes the rules by moving the power source off the ship, turning the spacecraft into a receiver rather than a furnace. A laser or microwave array in the home system pushes a light sail, letting the craft carry little fuel, and that is a profound advantage. This avoids the rocket equation and makes high speeds more plausible for small payloads, especially probes that can be wafer thin. It also turns the mission into an infrastructure project, because the beam must stay locked on target for years, and the transmitter must endure as long as the dream does. Beam divergence becomes the enemy at intergalactic distances, because light itself refuses to stay narrow. Diffraction spreads the beam, and keeping intensity high demands an aperture of astonishing size, perhaps spanning kilometers or more. Pointing accuracy must be exquisite, because a tiny angular error misses the sail entirely, and a miss at high power is not gentle. The sail must survive intense flux without tearing, melting, or charging into instability, while keeping its shape like a perfectly tensioned drumhead. Beam sails can launch fast probes, but braking at the destination is a second unsolved problem, and it waits at the far end like a locked door. You can brake with a second beam from the far side, but that assumes a transmitter already exists there, which turns exploration into colonization before arrival. You can use a magnetic sail to push against the interstellar medium, but the medium is too thin to provide strong deceleration quickly, especially at high speed. You can do a flyby and send data home, but then the mission becomes a single pass through a galaxy you cannot stop in, like reading one page as the book burns. The void turns arrival into a question as hard as departure, and it refuses to answer either one cleanly. Nuclear pulse propulsion sits between the plausible and the taboo, haunted by Cold War history and by the physics that still works. The idea is simple, and that simplicity is why it refuses to die, even after treaties and public fear. Detonate nuclear devices behind a pusher plate, absorb momentum through shock absorbers, and ride the explosions outward, each blast a brutal step. The specific impulse can exceed chemical rockets by orders of magnitude, and the thrust is high, which makes it attractive for heavy payloads. Visually, it is the most violent form of sailing, surfing on artificial suns. The constraints are political, environmental, and structural, and they stack rather than trade off. The pusher plate must survive repeated nuclear blasts without eroding away, while its coatings and ablation layers are consumed like sacrificial skin. The shock system must handle repetitive impulses for months or years, and it must do so without fatigue cracks that grow silently. The ship must carry thousands of devices, each one a complex machine that must work on schedule, and a misfire is not trivial. Nuclear pulse could reach deep space, but reaching a significant fraction of C remains uncertain, and the engineering would be unprecedented. All these propulsion concepts share a hidden requirement, and it is the requirement that quietly breaks budgets. They must accelerate a payload and then decelerate it, unless the mission accepts never stopping, never turning, never landing. A one-way probe can be lighter, but a crewed mission needs braking, redundancy, and margin is mass. Every kilogram of shielding, habitat, and repair equipment multiplies the propulsion burden because it must be pushed and then slowed down. The void punishes mass with exponential cruelty, and it does so without drama. Now introduce the intergalactic medium because emptiness is not safety at high speed, and the void has teeth. The space between galaxies is sparse, but it is not zero, and its thinness is deceptive. It contains hydrogen and helium ions, trace dust, cosmic rays, and magnetic fields, all diluted to near nothing. At low speeds, this is a vacuum. At 0.1 C and beyond, it becomes a particle accelerator aimed at your hull, and the hull becomes the target. A single proton at 0.1 C carries kinetic energy like a high-energy radiation hit, and it arrives with relentless frequency over millions of years. A stream of such particles becomes a constant sandblasting of ionizing damage, degrading electronics and embrittling materials atom by atom. Dust grains are worse because their mass turns speed into explosive impact energy, and the impact does not care how small the grain was. Even a microscopic grain at relativistic speed can punch craters, generate plasma, and spray secondary radiation through the structure. In a visualization, the ship's bow glows with invisible collisions, like a storm you cannot see. Shielding is not just thickness, it is strategy, because the wrong shield can make radiation worse. A simple metal wall stops some particles but creates showers of secondary radiation, turning one hit into many. Hydrogen-rich materials reduce secondary neutrons and can be more effective per mass, which is why water and plastics keep appearing in serious designs. A forward shield might be layered, with sacrificial bumpers and spacing to disperse impacts, and with voids that let debris expand before it reaches the pressure hull. At high gamma factors, even the best shield becomes heavy, and heavy means slower, and slower means longer exposure. Some proposals use electromagnetic or plasma shields to deflect charged particles, shaping a protective bubble ahead of the craft. That helps against ions, but it does little against neutral dust grains, which ignore fields until they vaporize on impact. A magnetic field strong enough to matter must be generated and maintained for centuries, and it must remain stable through component failures and repairs. The field interacts with the surrounding plasma, creating drag and instabilities that must be controlled, and control costs power. The void makes every protective system a second propulsion system, because it demands energy just to survive. Radiation exposure is not only from impacts, because space itself is radioactive in a slow, persistent way. Cosmic rays and high-energy particles permeate space, and long duration multiplies dose until it becomes a chronic condition rather than an event. A crewed ship needs mass shielding, active monitoring, and medical countermeasures that must work across generations, not just across missions. If the travelers are not human, the constraints change, but they do not vanish. Biology, whatever its form, must still resist ionization and cumulative damage, and even machines must resist bit flips and material degradation. Now make autonomy central, because no rescue is possible, and no spare parts depot waits in the dark. A mission lasting centuries to millions of years cannot be operated like a spacecraft, because spacecraft are extensions of a living ground team. It must be a self-sustaining ecosystem of machines and possibly minds, with maintenance as a way of life. Closed-loop life support must recycle air, water, and nutrients with near-perfect efficiency, and it must do so without drifting into failure. Any leak that is tolerable for a year becomes fatal over 1,000, and any contamination becomes an ecological coup. Reliability becomes the real propulsion, because the ship must keep functioning long after designers are dust. Components must be repairable, not merely durable, and the design must assume that everything will eventually break. The ship must carry raw materials, fabrication tools, and the knowledge to rebuild itself, from circuit boards to pressure seals. That implies advanced robotics, additive manufacturing, and fault-tolerant design at every level, with diagnostics that can explain failures in plain terms. A single-point failure is not an inconvenience. It is extinction in a place where help cannot arrive, and where the nearest workshop is a galaxy away. AI and robotic probes offer a different path, because machines can treat time as a parameter rather than a threat. A machine can tolerate long timescales, hibernation, and radiation better than a biological crew, and it can shut down to wait out storms. It can be smaller, lighter, and faster for the same energy, which makes every propulsion option less impossible. It can also be replicated, sending swarms instead of a single fragile arc, and redundancy becomes a philosophy rather than a backup plan. Yet autonomy raises a quiet question about purpose. If the travelers are machines, who is the mission for, and what counts as arrival? Generation ships confront the time problem by accepting it, and by turning the voyage into a moving habitat. Instead of outrunning the void, they live inside it, building a world that happens to be in transit. Multiple generations are born, work and die before arrival, and the destination becomes a cultural inheritance. This avoids extreme speeds and reduces shielding demands, but it creates a social and biological experiment with no precedent and no outside referee. The ship must be a stable world, with governance, culture and meaning that survives isolation, and with rituals that make maintenance feel sacred. A generation ship also faces genetic and ecological constraints, because small worlds are fragile worlds. Small populations risk inbreeding and loss of diversity, and the math of population genetics becomes as important as the math of delta V. Closed ecosystems can drift, collapse, or lock into unstable equilibria, where a minor change triggers cascading failure. Psychological stress accumulates when the destination is a story rather than a memory, and when the sky outside never changes except by instrument. The void does not only test engines, it tests whether a society can remain coherent without a horizon, and whether meaning can survive without new input. Suspended animation and hibernation are often offered as shortcuts, because they promise to compress the human problem into a technical one. They reduce life support loads and psychological burden, but they demand medical control we do not possess, including safe long-term preservation of organs and neural tissue. Even if possible, the ship still must operate reliably while the crew sleeps, and sleep is not maintenance. A sleeping crew cannot fix a broken radiator or a drifting attitude control system, and a small fault can grow into a fatal cascade. The void makes passive strategies risky, because it rewards vigilance and punishes neglect. Now address navigation, because there is no road in intergalactic space and no familiar skyline to steer by. Star trackers rely on recognizable patterns, but constellations distort over millions of years, and proper motions slowly rewrite the sky. The Milky Way itself changes, and the reference frame is not fixed, because the Sun and its neighbours orbit and drift. A ship must navigate through a moving gravitational landscape shaped by dark matter halos that we still cannot map precisely, and by baryonic structures that evolve in the meantime. In the visuals, the map is alive, with vectors and uncertainties that breathe. Pulsar navigation is one of the few beacons that can work across the void, because pulsars are nature's clocks carved into neutron stars. Millisecond pulsars emit stable, periodic signals that can serve as a galactic GPS, and their timing can be measured with exquisite precision. By timing multiple pulsars, a craft can triangulate its position and velocity, even when stars are too faint to be useful. Yet pulsars glitch, evolve, and require a catalogue that must be updated, and an update is hard when your signal takes ages to arrive. The ship must carry its own ephemerides and correct them over deep time, like a sailor updating charts while the ocean rearranges itself. Long baseline updates from home are limited by light speed, and light speed becomes tyranny at these distances. Even if the ship sends status reports, the reply arrives years later at interstellar ranges, and millions of years later at intergalactic ranges, by which time the ship may have changed course or changed purpose. Communication becomes archaeology in real time, messages exchanged between civilizations that may no longer exist. You do not steer a ship with two-way conversation. You launch it with a plan, and you accept that the plan will outlive you, and perhaps outlive your language. This is where the earlier uncertainty about Andromeda's halo becomes operational, because unknown gravity is not abstract when you must thread a trajectory. We still debate the true mass and shape of its dark matter envelope, and that shape affects trajectories and capture energies in the outskirts. Substructure in cold dark matter could perturb paths over long times, nudging a craft by tiny amounts that accumulate into large misses. Warm or self-interacting dark matter could smooth the field and change dynamical friction in the outskirts, altering how easily a ship can slow down. The void is not empty of gravity, and we do not fully know its texture, which means we cannot fully know our aim. The mission must therefore be adaptive, because prediction alone is too brittle across deep time. It needs sensors to measure local plasma, dust, and gravitational gradients, and to detect changes before they become disasters. It needs course correction capability that remains functional after millennia, with propellant reserves that are guarded like treasure. It needs decision-making that can handle unknowns without waiting for instructions, because instructions arrive too late to matter. Autonomy is not optional when the nearest command center is a million years behind, and when the ship's problems are happening now. Now return to the mystery, because the chapter's tension is not only technical, and it never was. The void is so hostile to human timelines that it invites a different kind of traveller, one whose patience is built into its design. A probe that thinks slowly could treat a million years as an acceptable cruise, waking occasionally to check its course and then sleeping again. A civilization that measures projects in geological epochs could see the journey as routine, like planting a forest, or the travellers could be something that does not age, does not breathe, and does not need a home planet's constant resupply, because home is a concept they outgrew. If the travellers are not human, the constraints shift in revealing ways, and the void becomes a filter for certain traits. A machine intelligence could accept extreme radiation and repair itself with stored feedstock, turning damage into a maintenance schedule. A post-biological society could compress minds into durable substrates and run them intermittently, spending most of the voyage as cold hardware. A distributed swarm could lose many members and still succeed, because success is statistical rather than personal. The void selects for persistence, redundancy, and patience, not for heroism, and that selection feels like a message.